What, as in go to like shops, as in getting food shops?
Yeah, getting food.
I mean, heck, that's tight.
Yeah.
I remember what I did. I think mine involved drinking cider, I think. Right, so it's maths again. Right, don't forget Samuel, maths again tomorrow. Right, so you need to do your sums. You need to know it all. Right, every single possible sum. Right, Farhan, we do need our camera on today. Thank you. What was the chemistry exam like?
Chemistry exam was like a little bit hard.
Yeah,
Like, it's very
yeah.
hard.
Every single person has said that the chemistry paper two has been the hardest one. I think combined was better, higher combined, but foundation and separates was hard. But the good thing is,
Unfortunate.
but everybody finds it hard though,
Yeah.
so it's not quite as bad. But tomorrow's maths.
Or as maths.
Well, as in there's lots of maths in physics,
Oh, oh, yeah.
right? So literally 30% of your exam tomorrow is going to be sums or graphs or whatever it is.
That's fine, but they give you the equations.
Yeah, yeah, yeah. Just those two equation ones that are a little bit harder.
Yeah.
Be fine. Right, we just wait for everybody to pile in. Right, can we try and put cameras on, please, everybody? It's actually quite hard for me just having Mac. I'm just looking at one person for the entire time, even though he's got lovely hair. Right, it's not the best. Okay, so Zara, I know you've sorted it out. Right, so can we try and get as many cameras on as we can, please? Right, so I can see you yawning and all that kind of stuff. Right, and getting ready for your party tomorrow. Hi, Maria. Okay, right, Adam. Daniel, get your camera on. Mario, get your camera on. Right now, while people are still kind of joining, right, don't forget your units. So I'm literally just going to leave that on for literally, I know, a minute. Okay, and during that time, you need to have a scan, right? Because don't forget, right, they are the things you're going to be converting to tomorrow. Hi, Florrie. Right, Alex, have you got a camera? Right, so on the screen, units. Scan them. Eva, camera. Mariam, Maria, camera, please. Farhan, you can come back on again now. Daniel, get your camera on. Sarah, get your camera on. All right, okay. All right, Maria, I'll let you off. Right, units. Right, check them. Okay. Right, now what I'm going to do first today is I'm going to go through the required practicals, right? Because the required practicals are pretty heavy, right? I think in this, in sort of the combined. Okay, so we're going to go through those first, right? But I'm just going to put that up again, right? So make sure you get that in your brain, right away from the top, right the way down to the bottom, right? Think about your conversions, right? So if you then get a conversion in your exam, right, I strongly suggest you just write down gut, muck, cut, muck, whatever, okay? And make sure you don't screw up any of your conversions. Times by 1,000 down, up by 1,000 divide. Right, Daniel, I can't see you. Lucas, get your camera on as well, please. Right. Okay, so what I'm going to do is I'm going to go through the required practicals. Okay. Now, they're a bit of a pain, right? Because there's kind of a fair bit of sort of thinking that you need to do, and there's kind of more than one part to most of them. All right. So we're going to start off with the waves one with the ripple tank. Okay. So when we're talking about the ripple tank, this equation at the top there, wave speed equals frequency times wavelength, is the equation that you're going to be working on, right? And vast majority of the time, what they're going to be looking for is they're going to be looking for you to calculate the frequency using the practical and the wavelength using the practical. Okay, so here you got a ripple tank, two different versions of it. Now, the one on the right, the top right, is the one off the syllabus. Okay, and then what I'm going to do is if I just kind of briefly mention it, and then I'm going to kind of go through the method that you're going to be doing. So usually, and they do vary quite a lot the way they can be. Sometimes you can have the light pointing upwards and it shines on the ceiling. This one, what you've got is here, you've got, it's about 0.5 centimeter deep of water, and you've got to make sure it's flat or it doesn't work properly. Okay. Then there's a wooden rod or a metal rod that goes across. And what that is, that's then connected up to a vibrating machine. Okay, what it does, it sets in sort of a certain frequency of vibrations. That then creates your waves. And then you got your light above. The light shines through the water, through the waves, and then underneath here, what you've then got is you've usually got a white piece of card, or you could have it on the ceiling, or the one that I've got at work, it kind of comes up on a screen at the front. And down the side, you've then got a metal ruler, or a wooden ruler, sorry, a meter ruler. Okay, right, so I'm going to go through kind of the method, right? And then what I'm going to do is I'm going to go through how we actually calculate things, right? So pour water to a depth of about 5 millimeters. So if they ask you to set it up, 5 millimeters, 0.5 centimeter, but it's got to be flat. Adjust the height of the wooden rod so it just touches the water surface. Okay. Switch on the overhead lamp and the electric motor. And then what you've got is you'll have a little dial on kind of your motor, and you adjust the speed of the motor, produce low frequencies. So then what you can do is you can see the waves. All right. If you can't see the waves, then that's no good. Okay, so just remember some of the depths. So 5 millimeters, a wooden rod, it's got to be flat, just touches the surface. Okay. Right. When you've actually got it set up, you place a meter ruler on the floor where the waves actually are. Okay, so if you look at the diagram on the bottom right-hand side, right, what those lines are there, they are all the waves that are then shining through from the ripple tank. Okay. What you've then got to do is the job number one is you've got to work out the wavelength. All right. Now, if you set it up correctly, what will happen is those lines will stay stationary. Okay. And so then what you do is you then get your ruler and you measure from one wave to a point where you can then sort of measure the waves. And if you're actually doing it as a method, you'll do it as 10 waves. You'll count the waves 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've got 10 waves. So then what you do is you do the distance. So if it's, let's say it's 75 centimeters, divide by the 10 waves will then give you your wavelength. Okay, so that's nice and straightforward. And don't forget what you'll probably have is you probably have a meter ruler line at the side of it. Okay. Another thing that some people then say is, as a potential, is get your mobile phone and take a camera of it, take a picture of it. If you can then take a picture of it, then you can do it very, very accurately on your mobile phone. All right. So that is how you work out wavelength. All right. Now, frequency is the number of waves per, frequency is the number of waves per second. So it's per second. All right. Now, if you've ever actually done this practical, right, it's very, very, very difficult to actually kind of time a second and count the number of waves. So with this one, ignore wavelength. What you're going to do is you're going to put a stop clock in the back. Right. You're going to put a point, a dot on the floor. Okay. Then what you're going to do is you're going to get your mobile phone. So this is a phone one again. You are then going to set your phone going on slow motion. And then what you'll do then is you'll leave your phone kind of going on slow motion, or just you do your phone as normal, right? And then what you do is you'll watch sort of 10 seconds go past. Then what you can do then is when you replay your phone kind of video, what you'll be able to do is you'll be able to count the number of waves that go past that point in 10 seconds. Okay, so repeat that again. You video it. You've got your stop clock in the background. And then what you do is then when you actually have videoed it, you get your camera back again. You put it on slow motion. Or however you do it. I don't know. It's too technical for me. Okay, and then what you do is you count the number of waves that go past that point in 10 seconds. And then you're going to do number of waves divided by 10, which is your seconds, which will then give you the number of waves per second. That is then your frequency. Okay, so that is then two ways or the ways in which you measure or calculate the frequency and the wavelength using a ripple tank. Right? Okay, now they could do it as a ripple tank in water, right? They could also do it as sort of waves in a solid. Okay, now the way this works is it works kind of very, very similar to a guitar string, right? Where this kind of piece of equipment that I've got on the screen this time, right? The black line that goes along there is your piece of string, okay? And it goes all the way down to these masses at the bottom there. And it literally acts like a guitar string. So if you pluck it, right, then what it'll do, it'll then create a wave. All right. Now, it works exactly the same, but this time what you've then got is you've got 100 grams of mass hanging off there. Okay. You've got your pulley, you've got a wooden bridge, which again is like a guitar. So the length of your actual piece of string that you're going to be working on is from the wooden bridge to where the vibration generator is. And then with this one, what you have to do is you have to adjust the vibration generator until you get something called a standing wave. All right. So you get your vibration generator, and then what you first turn it on, what it is, it looks like the string is just going mental. It looks kind of blurry. You adjust the vibration generator until it creates a standing wave, and the standing wave actually looks like that diagram at the bottom there. All right. It almost looks like it's kind of frozen in time, and you can see literally the wave sat in front of you. Okay. Right. Then you do exactly the same thing again. To work out the wavelength, you're going to go from the starting point of a wave to the end point of a wave. Now, if I draw a wave here, the wavelength can be from peak to peak, trough to trough, or it can be from that point there to that point there. It doesn't really matter where the actual wave is, all right, as long as it is from the same point on one wave to the same point on the next wave. Right? That is then your wavelength. Your frequency, says there at number 4, is provided for you on the signal generator. There's no calculation for the frequency this time. It is literally on the actual signal generator itself. So then what you can do, you've got your frequency from the generator, you've calculated your wavelength, you can then calculate the wave speed. Right, so they both work in exactly the same kind of way. And what they'll do is they could talk about a guitar, all right? They could talk about anything. Right. So that is then the wave ripple tank required practical. Okay. Right. Next one, radiation and absorption. Right. Now, yet again, with the physics required practicals that are kind of kicking in at the moment, so there's loads and loads of different variations that you can get. Okay. So this one that I've then got on the screen is kind of the standard one that you're then going to potentially see in your exam, and it's called a Leslie cube. Okay, now the way that a Leslie cube works is this is like a real picture in the bottom left hand corner here. It's got a hole at the top where you put boiling water. All the way around the outside, it's got 4 different kind of faces, and you put it onto a heat-proof mat. Okay, so the heat-proof mat is then to prevent heat loss through the base. All right. Now, the way that you do it is put your Leslie cube onto the heat-proof mat. Fill the cube with boiling water and put the lid on the cube. So literally what you're going to do is you're going to get a kettle, you're going to boil it, you're going to pour water down the hole at the top. Then you have to put the detector, the infrared radiation detector, let's say 10 centimeters from one face. So you've got your cube, you've then got your infrared detector 10 centimeters from one face, and you leave it there for 10 minutes, recording every minute. Okay, so I'll repeat it. You put the boiling water in the top, it's on a heat-proof mat to keep the heat in. You put your infrared detector 10 centimeters away. You can say 20, you can say 15, you can say whatever number you want as long as it's the same. You then start your stop clock. Every minute, record the amount of infrared radiation that is given out for 10 minutes. Then what you do is you do, so that side there, and then you do a second side, third side, fourth sides. So then what you're going to do is you're going to repeat for all the sides. Okay. Now, obviously, also what you've got to do is when you've done your first 10 minutes one, you've then got to make sure you empty out all the water out of the Leslie cube, and then you refill it again. Right? Because obviously you're not going to keep on carrying it on. Don't mess in class, stay calm. So dependent is your temperature change. That's what you're measuring. The independent is your surface. That's then what you're changing. And the control is the distance of the infrared detector. And it could be the time in between each measurement. And also the time that you may well then record your recordings over. Right? So that is then kind of option number 1, the Leslie cube. Right? And we'll go through some of the results. Now, again, what they could do is they could give you any color, any surface. Right? But literally what you've got to do is you just got to remember the order. Right? So this kind of graph at the top here, right? So silver is always the worst emitter, which means it is the one that cools down the slowest. Black is always the best emitter, which means it warms down the fastest. Right? So in your bedrooms, what you should all have black matte radiators. All right. Now, so it goes kind of silver, white, grey, black. Then interspersed in that, you're also going to have shiny and matte. So you'll have a shiny black and a matte black. You'll have a shiny grey, matte grey. You'll have a shiny white, matte white. I don't think you can get matte silver. Okay. And you've also got to remember then the best emitter of them all is matte black. Right? And above that shiny black, then matte grey, and that is then kind of the order. So they are then the best emitters. So you have a black radiator in your bedroom, that is the best. Okay, now there is literally tons and tons and tons of different variations that they can do, right? And what you've got to do is you just got to kind of manipulate what you can see, right? What they talk about, to use the logic about whether it's the best absorber or the best emitter. So on this experiment, it's showing the best emitter. Now, the best absorber is exactly the same. So the best emitter is matte black. The best absorber is also matte black. Okay, so the best emitter giving it out and the best absorber taking it in, they're both matte black. All right. So looking at a few kind of the variations that I sort of found, right? So if you look in the top left-hand corner here, right, what we've got there is got a Bunsen burner in the middle. On either side, there is a, I don't know, piece of paper, piece of wood, whatever it is. And if you see to the left, you've got a dark matte side. To the right, you've got a light shiny side. So it could be black, it could be white on the right. And on the back of it, there is a ball bearing stuck on with wax, both sides. And the experiment then is how long it takes for the Bunsen burner to make the ball bearing that's stuck with wax fall off. Right? One that I was used to use at school all the time. It looked like a bit like a propeller. Okay, and what you used to do is you used to heat up, put a Bunsen burner under this middle section here, and they were like metal thongs, metal sort of spokes sticking out. And you used to have a little bit of wax at the end of each one of them. Okay, with like a pin stuck on it. And it was the time it took for the pin to fall off. Right, bottom left, right, there's another version of the Leslie cube, where in the middle you've got an infrared heater. This is an absorber then, rather. Okay, and you've got a thermos flask that's black and a silvered thermos flask with an infrared heater in the middle. And then what you've got to do is you've got to think about which one is then going to go up the most. One on the right, okay, this is probably the second most common one that then comes up, where what you do then is you put hot water in again into each one of those beakers. They're all painted differently, right? And then what you do is you can then time how long, or do 10 minutes, and then you record the temperature each time. So it works very much as the Leslie cube, but then it's set up differently. Okay, so if you see anything with anything like matte black or shiny white or Leslie cube or hot water, it's going to be something to do with this. All right, but again, think about your control variables. You've got to make sure on this one in the bottom left-hand corner, they're the same distance apart. On this one on the right-hand side, you've got to make sure you put the same volume of water in every time. Okay, so make sure you're keeping everything kind of controlled, that you're not changing. All right. Right, force and extension. Okay, so this is now your spring one. Okay, now this is probably out of all of them, the kind of the most straightforward one. All right, so what you've got, hopefully you remember doing it. This is all about Hooke's law. Okay, Hooke's law, all about springs. Okay, so what you have on this is you have a clamp stand, and the first part of the clamp stand clamps a wooden ruler vertically. Then what you've got a spring, right? And when you put the spring down, what you do is you measure the original length using your ruler. Now, some methods might say that you have your ruler where 0 is there, right? Some methods might say it doesn't really matter where it is as long as you record it. So if that's 23, the original length where you're just hanging the spring without any masses on, and it says 23, you can then work out its extension. Right, so it says here the zero scale needs to be at the same height to the top of the spring. Doesn't really matter, okay, but it's probably a good thing to say. You take that reading and you put it onto a results table. Then what you do is you add 0.1 newtons, that is 10 grams. That is one of those little discs, 10 grams. Make sure it's not wobbling, and also make sure it's not touching the wooden ruler, because if it's touching the wooden ruler, then what it's doing is it's taking a bit of friction in. Take a reading on the ruler. That is then when the force is 0.1 newtons. Add further weights until you put 60 grams or 0.6 newtons on. All right. Now, there's a good reason for that. It all depends on your spring, but obviously if you then put too much weight on a spring, then it's going to damage it. Right. So take a reading of the unstretched spring. Add 10 grams. Measure the length or the extension with the 10 grams, which is 0.1 newtons. Add another 0.1 newtons, add another, do 6 of them. Record it on a table. Right? Then we've got the variables there. So the variables don't mess in class. We are measuring our extension. The independent is we are changing the weight. And the control is potentially the spring. Okay, and it's also the person who's doing it. Right? And there's another thing to make sure you remember. When you're actually recording the length of the spring, okay, don't forget your errors. Okay, because if you don't crouch down and look at your ruler exactly horizontal, you're introducing an error, which is then your systematic error, which is where you get it wrong every time. All right. Now, it's all about Hooke's law. So that equation there, F equals K times E, where force equals extension multiplied by spring constant. And again, when I put those units up all the time, right at the very start, remember your spring constant unit is newtons per meter. Right? Now, think about what that is actually saying. Right? So every single spring that exists in the entire world has got its own individual spring constant. Okay? So if you open up your biro and you've got one of those little springs in there, right, that'll be a little tiny spring and it'll have its own spring constant. And the spring constant is the amount of Newton meters or newtons per meter you can apply to it. Then you might have a really big fat spring in a car. That'll have its own spring constant as well. Right? So it's almost like a grading system of springs. Right, now, Hooke's law, and I'll show you the graph in a second. Hooke's law, this is a great kind of define question. The force on a spring is directly proportional to the extension provided the elastic limit is not exceeded. Right, so I'll explain that. There is the graph that you're going to get based on the practical I've just given you. So as the force increases, the extension increases. And it is directly proportional. Okay, so the extension is directly proportional to the force provided the elastic limit is not exceeded. Right, so remember, when you pull a spring too much, it stretches, and then the elastic or the spring doesn't go back to its original place. Right, so Hooke's law. The force on a spring is directly proportional to the extension provided the elastic limit is not exceeded. Right. Now, on there, what I've then done is I've kind of got a set of results. Okay. And what it does is it shows the first part agrees with, works with Hooke's law. So as the extension, well, the force increases, the extension increases. At that point there, where it then stops being a straight line, that is the point where the elastic limit has been passed. Okay, so that point there is the point where the elastic limit has been passed, and it will then be, the spring will be deformed and will not return to its original place. Okay, right, so that is the equation. Force equals extension, spring constant multiplied by extension. That is the equation you're going to get in this one. Right. Required practical number 4. Okay, so this one again, right, it's pretty heavy. Okay, so if you get yourself one of these questions, right, in each one of those required practical, there's a specific formula that is kind of used for each one. It'll be pretty straightforward for you, all right, but then just make sure you're kind of thinking about that. All right, now this equation is acceleration equals change in velocity divided by time taken to change. Okay, and again, they'll give you sums to do, and you'll then be able to work it out. Okay, now what I'm going to do to start off with is I'm just going to go through the equipment, right? Then I'm going to kind of mention the fact of the 2 different varieties, and then I'll go through each one variety in turn. Okay, so what we've got here is there is a car stationary. Between the car, there is a string that goes over a pulley to a weight stack. Right, the theory then is you let go of the weight stack, the car accelerates down the ramp, and then what you've then got to do is you've got to work out the change in velocity. Right, so there is 2 versions to this practical. In this top right hand corner, what I've done is I've just mentioned them, but then I'm going to go through them in a little bit more detail. So practical number 1 is where the mass stays constant. Okay, so what you're going to do is you're going to change the force, but the mass must stay the same. Okay, so I'm just going to clear all my gubbins off that, and then I'm going to actually put the proper method up in a second, right? But I think it's good just to kind of talk about it first. Right, so the first one I'm going to do is now where the mass stays constant, but you change the force. Okay, so what you do is you start off with a weight stack, right, that might have, let's say, 6 newtons on it. Okay, what you do is you let go of that weight stack, the toy car accelerates down the ramp. I'll talk about how you actually calculate the change in velocity in a minute. The toy car accelerates down the ramp. You record somehow the change in velocity, and then that's experiment number 1 done. Now the point in mass constant is you're now going to change the force, and instead of having 6 newtons on there, you're going to have 5 newtons. Okay, but the point of this now is that extra little disc that you've now taken off goes on top of the car. So therefore, the mass now stays the same for the car, the string, and the weight stack, because you've taken a weight off the weight stack and you've put it on top of the car. Okay. And also, one of the things that the examiners will often say is they will ask about the weight of the system, and everybody forgets about the string, because the string also has a mass. Okay, right, so clear that. Now what I'm going to do is I'm going to go to the method itself. Right, so this is now a constant mass. Right, so use a ruler to measure intervals on the bench. Attach the bench pulley to the end of the bench. They will do all that for you. Tie a length of string to the toy car or the trolley. Add a full weight stack of 100 grams. Okay, Now, this is then where you can actually work out the velocity. So what I'm going to do is I'm just going to flick double quickly back to this one. And what I'm going to do in the background is I'm going to put a stop clock. Okay, so that's a stop clock in the background. Okay. What I'm then going to do is I'm going to measure from there to there, and that is 1 meter. Okay. Then I'm going to get my mobile phone again. And when I've got my mobile phone, somebody then lets go of the weight stack. The toy car accelerates down. You have then got your video that you will then play back in slow motion. You've got the time in the background. So therefore, you can then work out speed equals distance divided by time. So your distance is 1 meter, and you've got your time that goes from there to there on your mobile phone on your stop clock. Right? Now, that is one way of doing it, because then what you've got is you've got your speed, which is basically the same as your velocity. And because it says change in velocity, at the start point it is naught. So then, once you've then got your change in velocity, you can then divide it by the time, which gives you the acceleration. All right? So that is one method of actually calculating the velocity. Another one, and you may well have this at school, is you can then have light gates. So a light gate is basically a little device that has a little beam of light going across the track. When the car breaks the light gate, the timer starts. When the car gets to the second light gate, the timer stops. And then what you've got is you've got your time. Okay? They may well pick on each one. Now, personally, right, what I would do is I would go for the mobile phone one where you record it, right? Because it's kind of a more kind of an advanced version, and it's probably more accurate. Right, that is then experiment number 1. Don't forget, after you've done experiment number 1, you transfer your mass from the weight stack to the toy car. Okay. Right, now the second experiment, it basically works exactly the same way, except this time what you're doing is you're keeping the force constant. So in the method I had in the other one, we had 100 grams, okay, which is 10 newtons. Okay, that stays the same. But this time what we do is we adjust the mass. And to adjust the mass, we then add on the masses onto the top of our car. Okay, so experiment number 2, the force stays constant. That never changes. But this time, you add masses to the car. So basically what you're doing then is you're getting the car heavier and heavier and heavier. Okay, that is then experiment number 2. Now I'll go through the method, talk about it again. Okay, and then what I'll do is I'll go back to kind of the graphs. Right, so method number 2. So what it says here, it says put 200 gram mass on the car. There it is, 200 grams. The weight stack at the end, right, is 100 grams or 1 Newton. Okay, so it's 100 grams, 1 Newton. Okay, I think I said 10 Newtons before, which is incorrect. So 100 grams, 1 Newton. You release the car, work out the velocity. And then what you can then do is then you can work out the acceleration because you've got the velocity. That's experiment number 1. Experiment number 2, because you added 200 grams mass to the car, then what you can do is you can take 20 off and then you have 180 grams on the car. But this time, the mass of the car is changing. Right. Now, I know I'm kind of jumping around here a little bit, but it's just got to be just dead clear that there's 2 methods. So I'm going to very, very quickly go back to the first one again. Okay, so the first one is constant mass. You move the mass from the weight stack onto the car. That's the constant mass part. Now, the graph looks like that. So when you've got constant mass, as the force increases, the acceleration increases, and it is directly proportional. So when the mass is the same, it is directly proportional because it is a straight line. Okay. The second experiment, where this time what you're doing is you're keeping the force the same and the mass increases. This time it is now inversely proportional because as the mass increases, the acceleration decreases, right? So think about it, right? In a year's time, some of you are going to be driving, okay? Even though you're not allowed other people in the car, which is relatively funny, okay? So what you then got is you got your car. Now, if you got your nan in the back, right, that's adding more mass, so you're not going to be accelerate as fast. Then when you got your nan in the car and then you got your granddad in the back of the car, you've got more mass again, so you're not going to accelerate as fast. Okay, right, now, they are the 4 required practicals. Okay, now if we've got time at the end, which I don't know if we will or not, okay, I'll go through them again, right, because, you know, they're going to get chosen. Now, what I'm going to do now is, I'm not planning on patronizing anybody, but what I need you to do is I just need to think about your equations. 30% of your exam tomorrow is again going to be on equations, right? And what I need you to do is I need to set it out. Okay. Now, again, you've already done exams, so therefore, right, you're all going to be pretty aware of it. Okay. But I'm just going to remind you of the structure that is good to get marks. All right. Firstly, highlight the numbers. Okay. Then underline what they're asking you to do. Okay, do that every single time, because then what that's doing is that's telling you exactly what sums you're going to be using. Okay, right. Then, even before you think about anything, convert. It's so easy to miss a conversion. And if you miss a conversion, it might only be 1 mark, because as long as your sums carry through, you'll probably be okay, right? But why take the risk? So if I look at that there, I'm then going to put 2.5 kilonewtons equals 2,500 newtons. And I know that's the conversion because that's that sheet I showed you right at the very start. Then there's another one. 500 grams equals 0.5 kilograms. Okay, so before you do any sums at all, remember conversions. Right? On higher, it's going to be right from the start. On separates, it's going to be right from the start. Foundation, it would probably be about the 4th question with numbers in it. All right. And the best way of kind of looking for that, you'll see it becomes a 4-mark question. Then, if you want to do the triangle, do the triangle. So that one is force equals mass times acceleration. So force equals mass times acceleration and force on the top. Make sure you write out your equation. So it's asking for acceleration. So I'm going to ignore acceleration. Acceleration equals force divided by mass. Write out your equation again, right? Because you don't get any marks at all on this convert bit unless you write out the correct equation. Then substitute. Force goes in, 2,500 divided by 0.5. Do another equals. Make sure it's nice and neat and clear. Don't be one of those people that just scrawls a load of stuff all over the place. 2,500 divided by 0.5. I think that's 5,000. Somebody will probably correct me if I'm wrong. Meters per second squared. Okay. Again, look out for sig fig. It'll be in bold, but if it said sig fig, hopefully you would have highlighted it in the question. It says decimal places. Again, it'll be in highlighted bold in the actual question itself. Okay, you might be thinking, I won't do that. Okay, but loads and loads of people do. Also, they seem to be doing a bit of standard form. So again, make sure that if it says it in the question, that's what you're going to do your answer. Okay, so that's just a reminder. Take your time, 30% of the marks. Right, now on to theory. Okay, right, so a force. A force is a push or a pull or a twist. Okay, they're not going to ask that, right? But it could be a force is a push, a pull, or a twist. Okay, could any of them just get it? Right. So, two types of force, contact force and non-contact force, right? It's reasonably self-explanatory in their names. So a contact force is where they touch. So friction, air resistance. You know, when you put your arm outside the car on the motorway and you kind of do like a little snaky dive thing. Okay, I do that all the time, even when I'm driving. Okay, tension. Tension is then when you're pulling on something, right? And then you get literally physical tension in the rope itself. They are contact forces. Non-contact forces are between objects without touching. So gravity. Gravity is pulling all of you down right now, okay? But you don't know it's there. You're not touching it. Electrostatic is your static electricity, and magnetic forces. Okay, so that train that's in Japan, the maglev, right? So a maglev train, magnetic levitation, is where the train doesn't actually touch the ground, right? Because what you got opposite poles, one on the track, one on the train, so they don't actually touch the ground. Okay, so they are non-contact forces. Right, now the other names to kind of think about is scalar and vector. Okay, again, they don't really ask particularly very much on this one, right? And if they do, it'll probably be a 1 mark or a 2 marker. So we just need to kind of have a little think about it. So a scalar quantity is just a number. So I've put magnitude there, but it is literally a number. Can't spell number. Okay, number. Right? Examples of that. Length. 57 centimeters is just a number. Mass. Again, it's just a number. Temperature is 22 degrees C. It's just a number. Right? Now, there's a few other examples on there, but if you then time's a great one in the fact that time is just a number. A vector is then where there is also a direction. Okay, and I'll give a couple of examples in a minute. All right. Well, I'll do an example now, right? So there's me at school. Okay, that's me teaching, right? And what there's loads of desks, okay, all over the place, right? There's some desks, right? And that guy there's got an exercise book I want. Okay, so what I could do is I could do the distance. The distance is me walking all the way around there. That is the distance I take. And that is a scalar. Okay, it's just a number. Displacement is the vector version of it. So my displacement would be climbing over all the desks going in a straight line. So displacement is a number, but it's got direction. Okay, so that's one example. I'll just give another example. Okay, because they're quite useful to think. Okay, right. Excuse me, didn't do my pen. Still didn't do my pen. Right, so up this board, there is an object traveling at 10 meters per second. Okay, so up the board, object traveling at 10 meters per second. Then what it does an immediate right turn, and its speed is still 10 meters per second, because that's how fast it's going. It's just a number. Then it takes another immediate right turn, and it goes down my board, again at 10 meters per second. Right, so everywhere on that kind of little diagram there, its speed is 10 meters per second. Okay, now the key to what I kind of then said was, I then said up my board. God, I can't even spell my board. Right, now velocity has a direction. So up my board, the velocity is 10 meters per second. Okay, that is the velocity up my board. It's a number with a direction. When it takes a right here, okay, so it takes a right, what is its velocity up my board now? 0 meters per second. So because I gave it a direction this time, because it now isn't going up my board at any velocity, it's taking a right, and its velocity up my board is now 0 meters per second. Then if you think about it, when it's going this journey here, its velocity up my board is minus 10 meters per second. Okay, so they are an example, sort of two typical examples of scalar and vector. Right. I'm not going to do that one. Okay, right. Force diagrams. Okay, now again, it's very, very unlikely that anybody's going to get to kind of draw any force diagrams. Okay, but again, you never know. So on the left-hand side, right, what I've got is I've got an aeroplane. Now the words change slightly. Okay, it changes kind of depending on what school and what book you read and things like that, right? But the main ones are weight is the force of gravity down. Drag is kind of like your air resistance. Thrust is kind of the acceleration one. The one that seems to change the most is lift, which tends to be in an aeroplane. And when I've got this car, it could be a reaction force going upwards. Okay. Now, with these diagrams, right, probably the most likely thing to do is you're going to have to resolve forces, right? And what I'm going to do is in a little bit, I'm going to talk a bit about that, how you actually do it. Okay, but again, if you look at my car on the right-hand side there, okay, it's not my car really, I've got a red one, all right, which is the biggest arrow? So the biggest arrow is the thrust to the right. So therefore, what you can think is if its thrust is to the right, that car is accelerating. Okay, so they're the main words. Weight down, thrust is forwards, drag, air resistance is to the left. You can also have friction in there as well, right? There's kind of a few different words that you can have put in there. Lift is often an aeroplane. Reaction force is then often with a car. Now, the other one that you then have is sometimes on a diagram, they might put the normal force, which is kind of more of a generic one. All right. Now, there's a car, right? Now, what they might do is they might say, draw a free body diagram. Now, this here is an example of kind of what a free body diagram looks like. And literally, all it is, it's exactly the same diagram, but you take away the object. And it's then kind of based on the arrows. So if you look, the green reaction force and the weight are the same. The friction is a certain amount, the thrust is a certain amount. And again, you can see with this car, it is accelerating because the thrust is to the right. Okay. Sometimes they also put a box in the middle there. So it says draw a free body diagram. That is then what you're going to do. It's just the arrows. Right, now, a little bit of Newton's law, and then soon enough, we're then going to talk about resolving forces. Okay, now, I think Newton's laws are pretty much down common sense, really. Okay, now, I don't think they're going to ask you to state any of Newton's laws, right? But again, they might. Right, so Newton's first law, right? An object cannot start, stop, or change direction by itself. Well done, Newton. I could never have worked that one out myself. All right, so you think about a box. It ain't going anywhere unless there's a force applied to it. So Newton's first law, an object cannot start, stop, or change direction by itself. Okay, tricky. Right, so that is Newton's first law. But again, they might do one of those funny little diagrams where it says Newton's first law and an arrow. Okay. Newton's second law, right? Now, Newton's second law is purely based on F equals ma. Force equals mass times acceleration. Okay. So the actual law itself states the force applied to an object is equal to the product of its mass and acceleration. So what you're doing there is really you're just kind of describing the equation. So Newton's second law, right? The force that you've got to put into that object is the mass times the acceleration. Okay. So what they might do in there is they might mention Newton's second law. Again, I'd be very surprised if they actually ask you what Newton's second law is, right? But then you may well get some sums based on it, right? So force equals mass times acceleration, right? Newton's second law, force equals mass times acceleration. Okay, right. Newton's third law, okay, I think is kind of more likely to get asked about. All right. Now, definition: for every action, there is an equal and opposite reaction. Okay. So the example I've got on the board there is there's a box. All right. That box is putting a force down. What is the floor doing? An equal and opposite reaction force. So that box is on the ground, it's applying a force to the ground, the floor is then applying a force back up. Okay. If I have a temper tantrum and I punch a wall with 1,000 newtons, that wall punches my hand back by 1,000 newtons. Right, now two kind of examples. That woman, right, she looks very chilled, okay, she is applying a force onto the wall. The equal and opposite reaction is the wall is then applying a force equally back at her. This boat, right? So you see all those YouTube videos where all the old ladies fall in the water, which is always funny. Okay, is this person is standing on the boat, and what they do is they jump that way. Their force going to the left is exactly the same as the force going to the right. Okay, so what will happen is they will move to the left and the boat will move to the right because it's an equal and opposite force. If you're into guns, all right, so what you do is you get a gun, right, and then you put it on your shoulder, right, and then you pull the trigger and the bullet comes out at 5,000 newtons. The recoil is 5,000 newtons into your shoulder, hence why supposedly it hurts. Okay, so you've got a gun, you pull the trigger, the bullet comes out at 5,000 newtons. The equal and opposite force is back into your shoulder, which is the recoil, 5,000 newtons. Right, so they are Newton's three laws. Okay, now what I'm going to do is just talk a little bit about resultant force. Now, for foundation, this is kind of all you really need to be able to do. Right, I will mention right at the very end, in case something that might be right at the far end of foundation, which could be using Pythagoras. Okay, but I'm going to leave that right at the end. Right, so a resultant force is a single force that has the same effect as two or more forces acting together. Okay, so if you get an object, right, that has different forces being applied to it, you've then got to work out what the resultant force. Resultant is the result, it's the answer. So on that pink box there, what I've got is I've got a force of 10 newtons left and a force of 20 newtons right. Right, so common sense says that there's more force going to the right, so therefore the resultant force 10 newtons right. Okay, and again, don't forget to put your direction in. You just say 10 newtons, it could mean anything. The blue box at the bottom, 15 right and 30 right. The result or the resultant force is 45 newtons right. Okay, so that is resultant force. It'll be pretty obvious when they're actually asking it because they'll give you numbers. Okay, I've just put this diagram randomly, right? Because I kind of put my PowerPoint through AI to ask if there was anything missing, right? And it said center of mass is mentioned on the syllabus. Okay, and I didn't have it in, right? So center of mass, okay, is where smack bang in the middle of whatever your object is. Okay, so if you were going to get a triangle and you're going to try and spin it on your finger, center of mass is the very, very center of the object. Center of mass. Okay. Right. Rocket. Right. So I'm going to go through rocket because again, this is kind of like a good forces thing. I'm going to kind of draw the stages onto the next slide. Okay, but what we've basically got is a rocket. Okay, and what the rocket's got, it's got thrust upwards, it's got drag, and it's got weight downwards. Right, so I'm going to kind of do it step by step. Number one is I have my rocket on the ground, and in stage one, all I've got is I've got the weight pointing downwards. Okay, so the weight on the launch pad is holding it down. Number two, then what happens, and I really can't draw rockets at all. Go do some little fins on that one. Okay, there it is. Now what we've got is we've got thrust, which is then going upwards, but our weight is still the same. So therefore, stage two, if the thrust is a bigger arrow, then the weight is going to accelerate upwards. Stage number three is then, as the rocket then continues upwards, the thrust is going to stay the same. The weight is going to stay the same. Okay. And then what you've got then is you've then got the drag starts to build up. Okay. And at this moment, you can still see the thrust is bigger than the drag plus the weight. So therefore, it's still accelerating. Number four, you've got your thrust up, you've got your drag down, you've got your weight down. Therefore, it is at a constant speed. Okay. Right. So that's a rocket. Now, mass and weight. Okay. So now, again, don't forget, with a rocket itself, it's going to be a lot more based on kind of lengths of arrows. Right. Mass and weight. This is, again, where people kind of make mistakes and stuff. Right. So what I'm going to do is I'm going to do mass and I'm going to do weight. Okay. Just to kind of explain the difference between them. All right. So there's me. Okay. And there is me again. In this room, I am 50 kilograms. Okay. And my weight in this room is 500 newtons. Right. Now, mass is all based on the particles. Okay. So it's all based on the particles. So therefore, in this room, what I've got is I've got 75 kilograms worth of particles. If I go to the moon, how many particles have I got? 50 kilograms worth. Okay. If I go to the sun, I've got 50 kilograms worth of particles. Weight. Weight is a force. Okay. So my weight in this room is 500 newtons. If I go to the top of Mount Everest, it's going to go down because I'm further away from the center of the Earth. If I go to the moon, where it's a third of the gravity, my weight will be, I know, I can't remember, work it out, 166 newtons. Okay. If I go to Saturn, where the gravity is bigger, my weight might be 5,000 newtons. Okay. It doesn't come up. Okay. Right. So mass and weight. Okay. Right. Next topic, refraction. Okay. Right. So what I've then got is refraction, right, is where we've got a beam of light and we have a glass block. Okay, it can be a perspex block, right? Can be a glass block. All right. So what happens with refraction is you get your incident ray coming in, right? It hits the glass block, and then what it does is it changes direction. Then when it leaves the glass block, it changes direction again. Now, what you've got to do is you've got to think about the reason why that might happen. So the incident ray hits the glass block, and what happens is the medium changes density. So if it goes from a low density to a higher density, it moves towards normal. Okay, so I'll just repeat that again. So you've got your incident ray, which is a beam of light. It touches the glass block, or it goes into the glass block, and because it's going from less dense to more dense, it turns towards the normal, which is kind of the bending of the light. It then goes a straight line through, and then because it's going from glass to air, it's going from more dense to less dense, so it turns away from the normal. That is then your emergent ray. Okay, so that is then refraction. Okay. Right, now this is then kind of like another sort of example where what we've got is on the left hand side, we've got deep water that then goes into shallow water. Okay, so when the wave's actually moving along in the deep water, when it gets to the shallow water, what happens is it slows down and then it changes direction again. So deep water, the wave is moving along. As it hits the shallow water, what happens is then the wave slows down and it changes direction. And you're also then going to see the waves actually getting bigger and appearing. Right? So that's kind of an example within water. Okay. Right. Distance time graphs. Right. So we're going to go through some of the graphs that are then involved. Okay. Right. On the screen, what we've then got is we've got distance time graph. What you can do is you can see distance down the left, time across the bottom. Okay. Now, the actual graph itself, right, you've got to then make sure that you're looking at it, right, and you are then seeing distance. All right. Excuse me a second. Anya, you just go away, right? Sorry, my daughter, she says she sent a code to my phone, all right? And now she wants my phone so she can get a code that she can then go onto it. But just go away. Was that a nice thing to say to my daughter? Go away. Right, go away. Right. Go away. Quick tip, everybody, never ever have kids. Okay? Or cats or anything like that. Okay. Right. So distance time graph. So what we've got now is we've got our distance time graph, and you've got to look at the axes. Okay. So the axes, distance down the left-hand side, time across the bottom. Right. And what they might do is they might ask you to kind of analyze the journey. So that red line there, okay, makes quite common sense, right? When it's going along, it's going at a constant speed. All right. So constant speed. Okay. And we can tell it's going at a constant speed because it's a straight line and it's getting further away. Okay, because if it wasn't getting further away, then you would have no idea what was going on. When it gets to the blue bit, that line there, it has then stopped, stationary. And we know that because it is now 30 kilometers away. Okay, so it stopped. It then starts up again. The green line is then faster. So it's a faster constant speed. The purple line shows a constant speed again, but at 2 o'clock in the afternoon, it has got back to its starting point. Right? So that is our distance time graph. Right? Now, if they ask you to calculate the speed at any point, remember speed equals distance divided by time. Right? So if they ask you to work out the speed on that initial red line, you would then draw yourself a triangle, and then you've got distance, which is then 30, divided by the time, which is 2 hours, convert it to minutes or seconds or whatever they're asking for. So that is then your 2 hours. Okay, you would then have to look for whatever conversion it is. One of the things that often people will get wrong is they might ask for the speed on that green line there. Right, and what you've got to remember here is you've got to go a triangle is well up there. So then that is then your distance from there to there, and your time is from there to there. Okay, so make sure you're not going to do it right the way from kind of the bottom, because then that isn't the distance it's actually traveled. All right. Now, there's another example, kind of a graph that you might get, right? Just be very, very careful about sort of the scales, okay? Because the scales can be a pain. So that one then is in meters. All right, and I've highlighted here again, if I want the distance for that line on the right-hand side there, that's your time. Your distance, that's not drawn very well, distance is there. So it doesn't go right the way down to the bottom. Right? Right, now what I've got is I've scribbled out distance on the left-hand side, okay, and I've changed it to speed. All right, now again, the reason why I do this is because what you've got then is you've got a graph that looks almost identical, but it tells you a completely different story. Okay, so speed on A, what's happening this time is the speed is getting faster. Therefore, it is accelerating and it is constant acceleration. Right? So make sure you're looking at the axes, because if the axis says distance, it's very different to speed, even if the graphs look very similar. B, it is going at a constant speed of 30 meters per second. So it is still moving. Green line, that is then going at a constant speed again, that is faster. The purple line is then decelerating, but we don't know where it arrives at the end, because all we know is it's gone accelerated, constant speed, accelerated, decelerated, but we don't know where it is. Okay, right, now that's kind of the same graph again. What I've then done is, but this time slightly differently. If they ask you to calculate the acceleration, what you're going to do is you will do that and that. You'll do the triangle there, because acceleration, that's a terrible color, because acceleration equals change in velocity over time taken. So what you can do is you can do change in velocity, which is from there to there, divided by the time taken to change, which is from there to there. Okay, so it'd be a good graphical one if they're not going to kind of give you a direct sum. The second thing you can work out on this graph is the area under the curve is the distance traveled. Okay, so if I wanted to know how far the object had traveled, okay, it is the area under it, which is that there. Okay, so what you then do is you can work out the area. Okay, right. They're the graphs, and literally what you've got to do then is you've just got to work out, right, what the graph is actually reading on the graph. Okay, so what numbers it is, what scale it is it meters per second, is it meters, kilometers, right? It's all kind of that sort of stuff. Right, now, again, another thing, when I put my PowerPoint into AI, it told me I haven't mentioned certain speeds. And in the actual syllabus itself, it actually tells a direct speed for walking, running, and cycling. Okay, now, however they're going to answer that, it might be a multi-choice question if you're lucky. It might be one of those little liney questions. So walking speed is 1.5 meters per second. Okay, which sounds to me pretty slow. Running is 3 meters per second. Again, which sounds pretty slow. That's about a 30-second, 100 meters. Cycling is 6 meters per second, okay, which again sounds really slow. However, if they've written them on the syllabus, you need to know those numbers. So walking 1.5 meters per second, running 3 meters per second, cycling 6 meters per second. Okay. Right. Now I put driving and trains and stuff like that on there again, right? But those numbers are not put into the actual curriculum itself. So they might be there, they might not. You'll just have to kind of work it out. But as long as you remember that basically cycling is 6 and the others are then slower, that kind of works. Okay. Right. We've just done velocity time graph. Okay, so here's another one that you might get asked. Okay, which is the same sort of graph, right? Except this time you've got your curve. So that is then a speed time graph. Now I think every single paper got a tangent on their papers for the last physics exam, right? So remember, if you are asked to draw a tangent, choose the place, choose the point that you're then asked for. It's not working. Okay, which is there, and then make sure that your tangent is equal distance from each side. Okay, so if you kind of hinted that there's a tangent, draw a tangent on and make sure it's touching in the right places. Right. Next little bit of a topic, okay, is inertia. Right, now this tends to be more of a higher one, right, and then it kind of follows with momentum. Right, so inertia is how difficult it is to change the velocity of an object. Okay, so inertia is how difficult it is to change the velocity of an object. Now, this and momentum are very, very similar, right? Now, inertia is basically based on its mass. So if you've got an object that is moving, okay, and it has got more mass, it's going to be harder to change its velocity. If you've got a lighter object, it's going to be easier to change its velocity. Okay, now that little van there, okay, it's got inertia, right? And what it's doing is it's heading in the right direction, okay, and then inertia is how difficult it is to change its direction. Another example of inertia is you've got a skateboard with a bowl of water on it. That bowl of water carries on, and because of inertia, the water continues to move. Right, so inertia and momentum, I'm going to talk about them, right, they are very, very similar. Right, skydiver, okay, which is again a fantastic kind of sort of example that they're going to chuck in. Right, so it's a bit like the rocket, right, where what you've got is you've got your different kind of lengths of arrows. So when a skydiver is sat in a plane, they're obviously not moving. When they jump out, weight is the main force that is then pulling them down. As they get faster and faster, the drag force starts to increase. What you can see on my diagram there, weight is kind of that red arrow, and that weight stays the same, which is the gravity. The drag force in section number 2 gradually gets bigger. And when drag and weight due to gravity are the same, that is a terminal velocity. All right. So the definition then of a terminal velocity is the maximum velocity attainable by an object as it falls through the air. Okay. Right. So that is then terminal velocity. And I think terminal velocity for a parachute is something like about 200 miles an hour. Okay, which is pretty quick. Okay, when you're plummeting towards the ground. All right. So terminal velocity, when they got their arms out, we're kind of flapping around. Okay, when they open up the parachute, all of a sudden what happens is they then have a huge air resistance drag. So then the actual arrow, or the drag this time, will be massive. That's when the parachute opens. As the person then slows down, eventually the drag, and they've opened the parachute, and the weight will then be exactly the same again. So then they'll float down at a second terminal velocity. Okay. Right. Oh yeah. There's a typical graph of it. Right. Again, they might sort of talk about and ask you to analyze it. Right. So when they jump out in this bottom left hand corner, there it's time 0. They will then accelerate. Okay, and eventually what they're doing is they are traveling at 50 meters per second. Then they're at a steady speed. Steady speed is terminal velocity. Open the parachute, velocity decreases massively to a second terminal velocity. Then they hit the ground. Okay, so that is a parachute jumping, or a parachutist jumping from an aeroplane. Right. Okay, just while I have a little swig. Right, stopping distances of a car. Okay, it's actually quite amazing how the examiners say, or exam boards say, that these are some of the worst answered questions. Okay, to do with stopping distance of a car. Right, so while I'm just having a little swig, right, think about what the thinking distance is, think about what the braking distance is, right, and then think about what the over-installed stopping distance could be. And then it's also factors that affect it. Right. Art time. Okay. Right. Now, I think this is then the part that people don't think, right? Because the stopping distance is the thinking distance added to the braking distance, right? And it's the thinking distance that people always forget about. Okay. So I leave my school, right? What I do is I get onto the main road outside my school, and a kid jumps out in front of me, right? Now, what you imagine is you just put on the brake straight away. Now, you don't. What you have to do subconsciously, right? You then think about putting the brake on. Okay, so what my car will do, it might travel that far before I start applying the brake. Now, you don't imagine that, right? You don't imagine that that's actually happening, but it actually is. And it only at that point there that I then apply the brake before I stop in front of that kid if I want to. If I don't want to, then I'll just keep going. Okay, and then it might save. Okay, so thinking distance added to braking distance is your stopping distance. Now, factors that affect. Okay, so there's another graph of it, sorry. Right, so your thinking distance, right, what you're doing is you're going along at exactly the same speed. Okay, because what you're doing is you are thinking about what might be happening, right? You're not sort of thinking there, shall I, shan't I? What you're going to do is your kind of almost reactions are going to be then controlling it. Then you get your braking distance. Now, main things that you're going to get asked about is factors that affect it. All right. So thinking distance is pretty much driver's reaction time. Okay. Now, just think about a few, right, that think might affect it. Alcohol, drugs, tired, age. Okay. They are kind of possible things. So in the real world, right, if me was driving a car and you were driving a car, you would stop it before me, right? Because you are younger, right? And you've got better reaction times. So thinking distance is affected by alcohol, which will obviously slow it down. Drugs will slow it down. Tiredness, mobile phones, somebody talking to you. Okay. And I think that's then where it all comes out with that when you lot pass your driving test, I don't think you're allowed anybody else in your car. Is it for a year? Something like that. Okay, so you've got to drive around on your own for a year, right? And I know that my daughter, when she passes, right, then I'm going to be teaching her how to drive. And when she then passes, even though I've taught her how to drive, I won't be allowed in the car with her for a year. She'll have to drive around on her own. Okay, but in a way, it does kind of make sense. It's all about reaction time and distractions. Braking distance is all to do with weather. It's raining, it's snowing, foggy, worn brakes or tyres. Hence why you have to have an MOT where you've got to have the exact right amount of tread on your tyres and that you get your brakes checked. The road surface, if it's gravelly, icy, wet, size of the braking force. Okay, if you've got a massive, great big 4x4, right, or you've got a little mini, right, the size of the braking force also has an impact. Okay, so factors affect the stopping distance, reaction times, which is your thinking distance, and your braking distances. Right. Right. Next little bit, momentum. Okay. Now, momentum is the tendency for an object to keep moving in the same direction. Okay. So what you got to do now is you got to think that I mentioned inertia before. Inertia is a scalar. So when I said that inertia, right, is the kind of almost like the tendency or the difficulty of stopping an object, that is a scalar, which means it is only a number. Okay, that is inertia. Momentum is a vector quantity. So momentum is the tendency of an object to keep moving in the same direction. Right? So if there was, let's say somebody was running through my house, right, and I pushed them, inertia is how much I slowed them down. If they're running through my house and I push them and they change direction, their momentum would be different, right, because they're not traveling in the same direction anymore. Okay, right, again, there's formulas, right, and also don't forget your unit. Unit of momentum is kilogram meters per second, right? Unit of momentum is kilograms meters per second, right? But if you think about it, right, your momentum, your unit of mass is kilogram, and your unit of velocity is meters per second. Okay, so if you do actually forget the unit of momentum, you can work it out because mass is in kilograms, velocity is meters per second. Basically, what you're doing is you times them together. So it's kilogram meters per second. Okay. Right, now, conservation of momentum. This will be a higher question or a separate question. Now, when two objects collide, the momentum they have before the collision and after the collision are the same, right? So there's two people. Okay, let's say I've got a momentum, I'm just going to make these numbers up, of 10, and that person has got a momentum of 2. So basically, I've got a momentum of 10 going in that direction, and they've got a momentum of 2 going in that direction. If I'm that person with 10, what I'm doing is I'm running along and I pick them up because they're only little. The momentum afterwards is 12. Okay, so this is again, it's a potential higher sum, right? But it could also be a foundation kind of question. So conservation of momentum means if two objects hit each other, the momentum they had before is equal to the momentum they have afterwards. Okay, another example, just to make you think, okay, is you've got a car. Okay, I can't draw cars very well, that's supposed to be a car, heading in that direction with a momentum of 30. Okay, I'm making these numbers up. You've then got another car heading in that direction with a momentum of 20. You can obviously tell that the momentum in that direction is bigger than that direction, and they hit each other head on. The car will move, or both cars will link together and they will move to the right with a momentum of 10. Okay, so you've got one car, head-on collision. Whichever car has got the most momentum is then going to move the crash. Okay, that kind of illustrates it again. This is kind of more what they do. Is you've got a red car and a green car. Okay, the red car's got a certain amount of momentum. The green car's got a certain amount of momentum. When they hit each other and they lock on, you add the momentums together and that takes it to the right. Okay, work done, right? It's just kind of a remember of it, really. So work done is, so it's talking about joules here, where 1 joule is 1 Newton per meter. So a joule is a Newton per meter. Okay, so if I was going to move a Newton 1 meter, I would use it 1 joule. But the main thing to remember about that one is the fact that work done is measured in energy, in joules. Okay, right, oops. Waves. Okay, so we're getting to waves. Okay, now it's a little bit blurry, right? And I've got other diagrams that are going to come up in a minute, right? So we've got waves. Now, I mentioned waves earlier with your ripple tank, okay? But what we've got here is we've now got a wavelength. Wavelength is from one point to another point at exactly the same place in the wave. Could be a peak to a peak. Could be a trough to a trough. Could be from that point there to that point there. Okay, that is wavelength. So it's from one point on a wave to the same point on the next wave. Amplitude. Amplitude is the height of the wave. And what the amplitude does, the amplitude gives it its volume. So the bigger the amplitude, if it's a sound wave, the bigger the amplitude, the louder it is. Okay, so for example, when I was your age, right, we didn't have iPhones and all these Alexas and stuff like that. We had a record player with your plastic disc on it, and we had an amp, right? And the amp was basically an amplifier. And the bigger the amp, the more amplitude it could give out, hence the bigger the volume. Wavelength, just talking about that. Okay, so if I've got a wave that is kind of like that, that's kind of my normal wave. If I've then got a wave that's like that, that is high pitch. Okay, high pitch meaning squeaky. If I then had another wave that was like that, that would then be low pitch. Okay, so you've got the normal. High pitch is where the wavelengths are then squished together. Low pitch is then when these waves are more separated out. If I then had this wave, that would be a high pitch wave because all the waves are squashed up. And because it's also got high amplitude, it would also be loud. Right. Frequency and period. Right. So frequency, we talked about that before, right? That is a number of waves per second. Right. So again, remember on the ripple tank experiment, you've probably got to work out the frequency, which is literally the number of waves that pass a certain point in 1 second. Okay, and remember when I talked about it, right? You then measure the distance of 10 waves, or how long it takes for 10 waves, or 10 seconds rather. Okay, and that is then the number of waves you divide by 10, and that is the number of waves per second. Period is the time taken to produce one complete wave. Right? On your equation sheet, right at the very end of your equation sheet, you have got the equation for period. So the equation for period is 1 over frequency. And you've also got your frequency equation as well. Okay, so look out for both of those. They're both on your equation sheet. Right. 2 types of wave. Okay, so we just talked about the first type of wave, which is the transverse wave, which is that one. Okay, transverse wave is light. Right? Now, another thing that you need to remember with that one is that you have on your actual transverse wave, right? The wave moves perpendicular. Okay, so the particles in a transverse wave move in perpendicular, right? So what you've got there is, if you look at any individual point on a wave, the particles are moving perpendicular, which means up and down. A longitudinal wave is then a little bit different. Okay, and what it does, it doesn't necessarily look like rings like that, but what it is, it's usually kind of lines. On a longitudinal wave, you've got something called a rarefaction, which is where there's not very many particles, and you have a compression where the particles are all squashed up. A rarefaction is where kind of the particles are spread out. Compression is then where the particles are all kind of squished together. A longitudinal wave example is sound. Okay, because what sound is kind of like the movement of particles. Now, where transverse wave, the particles move perpendicular, which is up and down, in a longitudinal wave, they move in parallel, which basically means they keep going backwards and forwards. Right? You probably saw at school the kind of videos of the slinky, you know, the big long spring. All right. So if you were then going to do kind of the slinky, right, with one of those waves and you do a transverse wave, you kind of move it sideways, right? And what you can do then, you can see the actual movement is perpendicular. With a sound wave, or you move it forwards and backwards, that is then when the particles move in parallel. Okay, right. Now, they could ask, I don't know, anything about the labeling of it or examples of it. So don't forget that a transverse wave is light and the electromagnetic spectrum. Okay, right. Now, you need to know the order of the electromagnetic spectrum. Okay, now I've got a little stupid mnemonic, right, which says rich men in Vegas use expensive gadgets. Right, now that's one of the lady teachers at my school made up that one. Okay, so rich men in Vegas use expensive gadgets. Okay, so what you got then is you got radio, microwave, infrared, visible, ultraviolet, X-ray, gamma. Right, and also what you've got is when you look at the actual electromagnetic wave, you've got your visible light in the middle. Okay, and they might talk about the visible light section. Okay, so where you've got infrared there, visible starts with red. Where you've got ultraviolet after it, that starts with violet. So it goes basically radio, microwave, infrared, red, orange, yellow, green, blue, indigo, violet, ultraviolet, X-ray, gamma. Okay, so that is then your electromagnetic wave. Right, dangers and uses. Okay, right, radio waves, right? You are all sat all over the country, right? And you are all getting bombarded by tens of thousands of radio waves per hour. Okay, they are safe. They are not going to hurt you at all. Okay, uses of them: communication, TV, radio. So if you haven't got digital TV and you still use a aerial on your roof, right, that is brought to you by radio waves. So if you're into CB radios or kind of walkie-talkie kind of things, right, they are radio waves. All right, microwaves. Microwaves burn if they are concentrated. Okay. Now, the main uses of microwaves are mobile phones, cooking, and satellites. Right. So what you got to do now is you got to think, right? Some of you are going to be using your mobile phones right now. In fact, I'm using my mobile phone right now. Right. For me to get a signal, it is based on microwaves. A few little things. Sometimes you go on like TikTok and YouTube and stuff like that. And what they do is they put like about 15 mobile phones around a piece of popcorn in the middle. right? And everybody rings that mobile phone all at the same time. On the actual videos, it shows that the heat gets hot enough to make that popcorn pop. Mobile phones, right, can cause cancer, okay, to a certain extent, or microwaves can. A number of years ago, there was a big scare in the fact that women were getting more breast cancer in the left breast than the right breast. Okay. And what it all ended up is the fact that they got their mobile phone in their right hand and they put it into a pocket on their left hand side. And then what's happening is all the mobile phone signals are going into this left hand side here, right? And there is a spike in left breast cancer. Okay. So it's just kind of, I don't know, a bit of a fact, right? So now I think people put them in their jean pockets. So now everybody's going to get right bum cancer. Okay. Right. Infrared. Okay. So infrared is, again, burning, right? Because what you've got to do is you've got to think, if you're sat in front of a fire, you are getting infrared radiation. Infrared is used for heating, remote controls, and cooking. All right, so if you pick up your remote control, right, what it is, it's giving out some form of infrared beam. Again, you get infrared cameras. You know, the police will have infrared cameras, and what they'll do is they will then look for body heat. Again, it's a kind of another kind of silly anecdote, but it kind of might remember it. 4 blokes in a car, right, having a car chase. Those 4 blokes crash the car because they're really nice guys, right? All 4 separate off. 3 of them are caught very, very quickly. One of them disappears down a back alley that's full of metal bins. And what happens is the police helicopters above with the infrared camera. And what they do is they see one of the bins has got slightly warmer, right? Based on the infrared camera. So the police go over to the bin that is slightly warmer and they find the young lad in the bin, right? And what his body heat had actually done is actually heated it up. All right. Visible light. Okay, so visible light, it can cause damage. Okay, if you've obviously got too much of it, okay, can cause damage to your eyes, too bright. Think about looking at the sun, right? If you look at the sun, I'm not quite sure whether it's all about the visible light, but then that can cause damage to your retina. Visible light, illumination, photography, fiber optics. Okay, so basically what a fiber optic cable is, it's like a glass cable, right? And going down that glass cable is visible light. UV light, right? Again, think about the actual spectrum itself. This is now after, we can't see it. Biggest issues with UV light, sunburn, and it can cause cancer. Okay, so if you're one of those people, right, that goes on sunbeds all the time, then what you're going to do is you're going to get bombarded with UV, right? And that UV is going to ionize the cells, the DNA, and then it can potentially cause skin cancer. Uses, security marking. So you can get like a UV pen and you can write all over the back of your TV and you can't see it, right? But when the robbers take it, then they can shine a UV light on it, and that UV light then will show the wording. UV light is used to disinfect water. So when we were talking about kind of purity of water in the last one, right, one of the things that they use is ultraviolet light and chlorine. Police use ultraviolet light to look at kind of rape scenes and things like that, where sort of men's bodily fluids, right, if a certain powder is put on them, will glow in UV light. If you go nightclubbing, right, nightclubs will often have a UV light at the entrance. And the idea of the UV light then is to make white shine, right? So even if your teeth aren't perfectly white, it looks like your teeth are dead white and your eyes are white to make you look better when you're walking down. And it also highlights all the dandruff over everybody's shoulders, which is lovely. X-ray, broken bones, airport security. So every time you walk through airport security, you are then getting a very, very small dose of X-rays. Gamma is used for sterilizing. So before an operation, all the equipment that's used to cut you open, right, goes through gamma to sterilize it. It's also used for detecting and killing cancer. So previously, where we've talked about kind of radioactive substances, gamma radiation goes into you, And then because it's got very sort of penetrating, it comes straight out, it can be detected very easily. Dangers, mutations, cancer. So even though gamma and X-rays can cause cancer, they are often, particularly gamma, is used to cure cancer. Right. Magnets. Okay, so we're getting well and truly kind of towards the last few individual topics. Right, so we've now got magnets. Biggest magnet, Earth. Okay, so what we've then got is we have a north magnetic pole and we have a south magnetic pole. Now, the north magnetic pole and the geographical poles are in different places, right? So if you followed your compass exactly to the north magnetic pole, you would not be at the geographical north. Okay, it's slightly off. And then the reason why you actually have a magnetic north is because the Earth is spinning, and in the center of the Earth, you've got an iron core. And that iron core is then spinning at a different speed, which then creates a magnetic field. Okay, so Earth is the biggest magnetic field. And I'm going to highlight it now, and I'm going to kind of say it again, but all magnetic field lines go from the North Pole to the South Pole, right? A few years ago, there's a question that was asked about where you actually draw the field lines on, right? And so what people did is they drew all the field lines on nice and pretty, but they didn't put the arrows on. And you've got to remember that the arrows go from the north to the south, and that is then the direction of your arrows. Okay. Other types of magnets, you've got a permanent magnet. Okay, so a permanent magnet is one that you'll get in your science room at school. Okay, which is like a red end and it's got a blue end. They are a permanent magnet. They then stay there. Now, another kind of sort of factual part about a permanent magnet: to take away the magnetism, you either heat it or hit it. Okay, so if you've got a permanent magnet and you heat it up, the magnetism goes away. If you've got a permanent magnet and you keep on hitting it, the magnetism also goes away. Now, what a permanent magnet can do is it can induce magnetism into something else. So again, when I haven't got a magnet with me, but if I then had a magnet and there were some paper clips on my table, those paper clips are not magnetic. So what I could do is I could bring my magnet to those paper clips, it would pick up those paper clips, and then the paper clips would then become induced magnetism, which then means they've got their own kind of magnetism in there. Okay. There are some other kind of diagrams, right? But again, if you get asked to draw kind of the field lines, I'll be relatively shocked, right? But north to south. If you are, or if you're given them, draw your arrows north to south every single time, right? Plotting compasses, again, you might have been given these in school, where what you've got at the bottom there, you've got the north and the south, that's your permanent magnet, okay? And you can see the little arrows on the plotting compasses. So these are just little tiny compasses, probably about a penny in size. What you can do is you can spread them out around the magnet, and then what it'll do the field lines. Okay, and again, you can see the direction that they're all going. Each one of the little plotting compasses is going from the north to the south. Going on, next little bit is we then have a wire, and if you pass current through a wire, you get a magnetic field. So this diagram on the left-hand side is just a wire going up the middle, right? And then there's no electricity passing through it, right? So what you can then do is you can see all the plotting compasses are pointing towards the north. If I then put current through that wire, that current creates a magnetic field in the wire. And then what you can do is you can see all of the plotting compasses then change direction or start moving. Right? Now that is, or it can be worked out by something called the right-hand grip rule. Okay, so what you do with that one is you can see it on the diagram there. okay, is if you grab the wire, right, with your right hand, you then work out which way the current is going. So on that example that I've got there is the current is going upwards. That will then tell you that the magnetic field is then going anti-clockwise. It's going this way. Right? And then what you can do, then you can probably imagine that if I then swapped the current round and my thumb then went down, the magnetic field is then going to change direction. Okay? Unusual that one to come up. Okay, the other hand is the one that will come up. Okay, so the right hand grip rule. So that tells you the direction of the magnetic field if you've got a single wire. Right. Okay, now heading towards electromagnets. Right, now the first thing is a solenoid. Right, so what I'm going to do is I'm just going to draw a solenoid. This is a solenoid. Oh, what's it doing yellow like that for? Or pen? A solenoid is that. Okay, it's a coil of wire with current passing through it. Okay, that's all a solenoid is. A coil of wire with current passing through it. Right, and what they do is they then have a magnetic field, right? And then what we can then do is we can turn the solenoid into an electromagnet. To turn a solenoid, which is just a coil of wire, into an electromagnet, right? What you do is, I'll just put them on. What you do is, first thing, you use an iron core down the middle. So what you've got here on this diagram is you've got your green wire is your solenoid. So the green wire is your solenoid. To turn it into an electromagnet, what you do is you put an iron core down the middle, which then makes it into an electromagnet. The next question will be then is, how do you make it stronger? To make it stronger, number one, you use a larger current. So the more current, the stronger the electromagnet. Number two, more turns. Okay, so if you go from 10 turns to 40 turns, your electromagnet gets stronger. Number three, put the turns of the wire together. So if you squish them up so they're all kind of crushed next to each other, the electromagnet gets stronger. Okay, so just to repeat it, a solenoid is literally a coil of wire with current passing through it. If I want to turn that solenoid into an electromagnet, what I'm going to do is I'm going to put an iron core down the middle like a nail. Then, to increase the strength of the electromagnet, I'm going to put more current, more coils, and put the coils closer together. Okay, that will then increase the strength of my electromagnet. Okay, right. Now, we have literally got about 3 or 4 individual little topics left. Okay, now what I've put on here then is I put on the fact that motor effect is mostly higher. Okay, now even though in the syllabus it says it's higher, foundation questions have come up where they've kind of shown a picture of the actual motor itself. So it's probably worth, right, those people that are still doing foundation, right, just to listen into this. And then what I'm going to do is I'm going to flick back up the required practicals. Okay. Right, so motor effect. This is then our motor. And what you've got on the left-hand side, you've got a north, and on the right-hand side, you've got a south. The green line shows the current. The black line shows the force. Down at the bottom, what you've got is you've got something called a split ring commutator, okay, which sounds a bit like something you might get after a very bad curry. Okay, so split ring commutator. right? Now, the whole idea of a split ring commutator is every half turn, it changes the direction of the current. Okay, so just repeat it again, right? That green line shows the current. The black line shows the force. And north to south is the magnetic field. Okay, right. Now, Fleming's left-hand rule. I've never ever seen this on a foundation paper. Okay, however, you again never know. So Fleming's left-hand rule. So however you remember it, thrust is basically the movement is your thumb. First field, second current. Okay, so thumb is the movement, first finger the field, second finger the current. Okay, so if I go back to the diagram here, right? So first finger field, so put it kind of in front of the screen and just have a good think about it. Second finger is the current. So then what you've got to do is you've got to think about the way that the current is then going. Thumb is then the force. All right, it's always good when you see one of these questions come up in the exam hall, because then you see everybody kind of doing this in the exam hall, and it looks kind of quite funny. All right, so just remember that. Force or thrust is your thumb. First finger, field, that's the magnetic field. Second finger is the direction of the current. Okay, right. Final two little things. Right, now this part is potentially mostly higher, but again, you just never know. Right, now remember when we were talking earlier about resolving forces, where we had two squares, okay, and we had 10 newtons in that direction. Sorry, one square, we had 10 newtons in that direction, and we also had 20 newtons in that direction. Not doing that. 20 newtons also in that direction. Right, then to resolve the forces, they're both going 30 newtons to the right. Okay, now the extra kind of hardish bit that they may well have is they might give you a picture where instead of you having two forces going in the same direction or opposite to each other, they might have the forces going at right angles, which basically means you've got a force of 5 newtons going to the right, 10 newtons going up. And to answer one like that, you then need to use Pythagoras. All right, but you've just got to kind of look out for it. So if it's going at 90 degrees, you're talking Pythagoras. The extra bit that is definitely higher, okay, is resolving forces, where what they'll do is they'll expect you to use trigonometry. Okay, where what you'll have is you'll have a force going in that direction, and then you'll have another force, but they'll give you an angle. If they then start to give you an angle, then you are then looking at trig. Okay, that is 100% higher only. Right. Now, what I'm going to do, I am literally going to fly all the way back. Okay, I'm going to fly all the way back. Right, I'm just going to stop sharing, mainly because there's a stupid picture on my screen. Okay, and I'm going to go back up to the required practicals. Right, and I'm going to very, very quickly go through them again. Right, because there's going to be questions on these. Right, ripple tank. Okay, so you've got your ripple tank. Remember, you've got 0.5 centimeter of water. Light shines through the water onto a screen at the bottom. They're going to ask you to calculate two things: frequency and wavelength. To work out the frequency, what you need to do is, work out the wavelength. You're going to freeze the picture. You can take a picture with your mobile phone, measure or look at, using the wooden ruler, a meter and work out how many waves are within a meter, or how far is 10 waves. And what you can then do is you can then work out the mean, because you've got 10 waves equals 17 centimeters. So therefore, one wave will be 17 divided by 10. Frequency, use your mobile phone again with a stop clock in the background, where what you're then going to do is you're going to record it. You can then see the number of waves passing by a certain point, and because you've got your stop clock in the background, you can do 10 seconds. You can then do it in slow motion. You can count the number of waves going past a certain point in 10 seconds. Divide that number by 10. Okay, and then what you'll do is then you have your frequency. Second one, radiation and absorption, Leslie cube. Pour water in, have your infrared detector 10 centimeters away. Then record it every minute, the amount of infrared that's coming out of it, put it in a results table, plot it on a graph. And remember, black matte is the best emitter and the worst absorber. No, the best emitter and the best absorber. So it gives out heat the best and it takes in heat the best. Silver is the worst emitter, so it doesn't give out heat, and it is the worst absorber. Different versions, just look at what they give you. Hooke's law, you've got your spring. Make sure you measure the sort of stretched spring to start off with. Add on 10 grams, which is 0.1 of a Newton. Plot it on your result, put it on your table, then do it again, 10 grams, then 10 grams down to 60 grams. You will then get a graph that looks like that, where extension is directly proportional to force. As soon as it passes the elastic limit, it becomes deformed, and you can tell where that point is because that's when the graph starts to curve, and that is where it reaches its limit of proportionality and it's past its elastic limit. Okay. Acceleration, I'm not going to go through all the details of these again. Okay. Oh, what am I doing? Why didn't somebody tell me before? I stopped sharing, didn't I? Thank you, Maria. Okay, so acceleration is then you've got the two practicals that come up: mass constant, force constant. If they start talking about constant mass, it's the mass of the car, the spring, and the weight stack. And if you take masses off the weight stack, they have to go on top of the car, so the mass stays the same. If they say force is constant, that means the weight stack stays the same, but then you either add or take masses off your car, because the car then gets heavier. Okay, right. With that one, if you've got constant mass, it is directly proportional, and that kind of makes sense. If you've then got a force stays the same, but what you do is you add more mass, you then get a graph that looks like this, which is then inversely proportional. Okay, right, now, before I say for combine to disappear, all right, make sure, right, that when you're doing your sums, you take your time and you make sure that you are then sort of making it look as clear and obvious as you possibly can. Highlight the data, underline what it's asking you, then think convert. You might not have to convert anything. Think convert, write down your conversions, then start dealing with your formula. you want to do the triangle, do the triangle. Again, when I've done this here, I've written my formula. Don't write it as A equals F over M. Write it in full words. Then put your equal signs underneath so it's nice and clear. And look out for sig figs, decimal places, and standard form. Right? But just take your time. Right? And also, don't forget, at the end of the higher paper, there will be a 2-equation question again. Okay, and you'll know it's a 2-equation question because it'll be 6 marks or 5. Okay, so read the questions. Right, does anybody have any questions about any of it? Right, before everybody goes, right, I want you all to put your cameras on, please. Farhan, Daniel, Alex, Maria, Zara, Mariam, Zishan, Farhan. Put them on. What are they doing? Thank you, Daniel. Alex, Maria, Zara, Mariam, Zishan. Zishan, I know yours works because it always does. Right, anyway, it doesn't matter. All right. Now, the point of the matter is now what you've got to do now is you've just got to go in and you've just got to read the question, read the full question. Okay. And make sure every single little thing that that question is then asking you, you are then writing down in your exam. Okay. Make sure you do all of that. Okay. Now, for when combined literally disappear in about the next minute, right? Very, very well done, every single one of you. Okay. You've all thought and you can see huge improvements. Okay. I think, Maria, you started back in September, right? And the difference basically from September to now is phenomenal, right? And that pretty much applies to everybody. So seriously well done, right? And also on results day, right? Before you tell your parents your science result, message me. Okay, because it's more important that I know than your parents, obviously. Okay, or maybe do it second. All right, but I do need to know what you did get. Okay, because I am genuinely excited for you. Okay, like I've said previously, at 8:15 or 8:10, right, I will probably still be online. So if there are any other questions that anybody needs to ask, right, then just log back on. But if you don't need to, all right, then good luck tomorrow. Last one. Okay, and then have a good time after it. Thank you very much, everybody.
Thank you, bye.
Okay.
Thank you.
Thank you,
Bye.
You cold, Farhan?
Yeah, pretty cold.
You cold, right? Or is it a fashion statement now?
Yeah, both. Both.
Both. Right. Okay. Right. Now, physics paper 2, right? Obviously, right? We've then got our separate stuff. Okay. Now, there isn't actually as much separate stuff in this topic, okay, as quite a lot of the others. Right. So, what we're obviously going to do is we're going to go through, right, separate stuff, right? And then if there is, what's going on here now, right? If there is anything that anybody then needs to kind of ask, then what we can do is we can try and go through it. Okay. If I can get my computer working properly. Right, so while I'm just faffing around, right, has anybody got any questions about any of the combined stuff? Okay, I think it's reasonably straightforward. All right, all the kind of stuff. It's kind of a bit more logical. I think the chemistry paper, all right, nationally was reported as being pretty tough. Okay, but if you then are sitting there thinking that it was all right, okay, then well done, right? But nationally, people said it was probably the hardest of the 5 so far. Okay, Adam's eyes are going to pop out of his head. All right, so you obviously don't think it was.
I mean, like the 6 marker was like, I mean, it's not like the questions were itself were difficult. I mean, if you studied like the content, It's quite straightforward.
Yeah. Well, I can't remember what the 6 marker was. What was it?
This food additive is made of sodium carbonate.
Oh,
Then they
yeah.
give you a list of all the stuff you need. How do you test for each?
Oh, yeah.
So
Because they actually did they did all the gas tests and everything, didn't they?
yeah,
Yeah, right. Yeah, but people nationally said it was hard. And the actual chemistry foundation paper, right, they all came out of that saying it was hard on the combined. Right. Now, you guys, if you saw one of those, you would think that's like the easiest thing you've ever seen in your whole life. Okay, but compared to all that. Right. So, paper 6. Right. So, what I'm going to do now is I'm going to kind of go through sort of the theory stuff. All right. And again, like I said on the combined one, what I've done is the PowerPoint that I would use for revision this year, I've then chucked it through AI that's then connected to the syllabus, right? And literally what it's done is it's tried to pick out every single little thing I didn't have on it, right? And then what I've done is I've kind of included examples of it. Okay. Right. So a moment. Now, remember, a moment, its unit is Newton meters. Okay, so it is on the little kind of unit sheets that I give all the time, right? It is moment Newton meters, right? It's one that very, very rarely comes up. Okay, so moment is Newton meters. Okay, so basically a moment, and it's reasonably kind of obvious, sort of the way that it works. So what you've got is you have a moment is the movement of an object around a fixed point. Okay, and what I'm going to do in a second is I'll give you a few examples. All right. Again, it makes sense, doesn't it? Right. If you go to the park, right, I know you'll all still go to the park and you'll kind of play on the swings and the seesaws and stuff like that. Right. If you've got somebody heavier, they're obviously going to be closer to the pivot point. There's your equation. Right. And quite often what they're going to do is they're going to make you think force times distance equals force times distance. Right. What they'll do is they'll just get you to try and work out force. Okay. But a moment is the rotation of an object around a fixed point. Okay. So if you've got a spanner and you're trying to undo a nut on something, right, the moment is the movement of the spanner when you've got the nut on one end. That is the moment. Okay. And then if you want to increase the moment, then what you do is you get a longer spanner. So therefore, your distance gets bigger. Okay. Levers. Now, I don't think they're going to ask particularly about levers themselves, about whether they're first class, second class, or third class, right? But what you just got to do a little bit is you just got to have a think about the way that levers work. Okay. So if you look at first class, right, what you've then got is you've kind of got your fulcrum, which is kind of the pivot point, and your pivot point is then in the middle. Okay. So you can see on the scissors, the pivot point, a bit like a seesaw, is in the middle, and then you've got effort on one side and you've got force on the other side. Right? So if you then apply force on those scissors there, effort on on there and force there, then they're going to be pretty much the same because you've got a pivot point in the middle. Second class is then like a wheelbarrow, where what you've got then is you've got the fulcrum at the front. Right? And then the force is in the middle, and the effort is then at the end. Now, the reason why you can still pick up a wheelbarrow relatively easily is because there's a long handle that comes out there. And that effort in that big long handle allows you to then pick up the actual mass, even though the fulcrum is at the front. Nutcrackers, right? Again, Nutcrackers works on a second level one, where you've got your pivot point right at the very end, and you've got your force in the middle. Okay, your effort then it goes on the handle, and obviously the longer the handles you've got, the more crushing power you've got. The third one, right, is the least efficient by a very, very, very long way. Right? So in a way, these could be chopsticks. Okay, now if you choose chopsticks, all right, so you're holding chopsticks, you actually, and I'm terrible at it, you actually have to have quite a lot of effort in your fingers, right, to actually make the chopsticks go together. So your effort is a long way away, and the force is then considerably less than the amount of effort you're actually putting in. Okay. Now, the best example of that one is your arms. Okay. So when you've actually got, or you're picking up a weight, the pivot point is your elbow. The muscles are creating the effort to lift up your arm. Right. So ideally, if we were kind of sort of made again, right, your muscle really should go from your shoulder to your wrist. Okay. That would then make it a lot better and a lot easier to pick up. Right. So they are then 3 different types of levers. Right. Now, I don't think they're going to ask you about the class of them. Right. But they might kind of mention something to do with levers. And think about which is the most efficient. First class is the best. Second class is then the next. And third class is very, very inefficient. Chopsticks, your arm. Okay. Right. Pressure. Okay. Now, pressure to me makes complete and utter logical sense. Okay. So if you've got a load of water in a container, right, you're going to have high pressure at the bottom because there's more weight being applied by particles from above. Makes absolute sense, right? That submarine that got crushed however many years ago it was, right? If you think about how far they went down and the amount of water above it that was then crushing it, okay, kind of makes sense, doesn't it? That it actually ended up collapsing, right? So the pressure at a given point is caused by the weight of all the fluid above that point, right? That's kind of your definition to think about. The pressure in water at a given point is caused by the weight of all of the fluid above that point. All right? That is called hydrostatic pressure. Okay? Hydrostatic. Think about the wording. Hydro, water, static, stationary. Okay? So that is hydrostatic pressure. Right? Now, I don't know why that's so blurry, okay, but that hydrostatic pressure is the reason why there is also upthrust. Okay, so upthrust, we all kind of know what that is, right? So if you get a cork and you push it down, it's got upthrust. If you immerse an object in a liquid, the pressure increases with the depth, right? And as you push it further down, there's more pressure. And that pressure on the outside of that object causes the object to go up. That is then the upthrust. Okay. Atmospheric pressure works exactly the same way as water pressure. Okay, again, it makes logical sense, doesn't it? It makes logical sense that where we're sat right now, there's going to be more particles because the particles are heavy and they're squashing down. As you go further up, there's going to be less particles. Okay, so therefore, right, atmospheric pressure decreases. And I think I mentioned before that at the top of Mount Everest, right, water boils at something like 75 degrees C, right, because there is less atmospheric pressure up there. Again, it kind of makes logical sense, right? So the more molecules, the denser it is, the more atmospheric pressure. As you go up, you've got less molecules, therefore it's less dense, therefore there is less atmospheric pressure. Okay. Right, now, electromagnetism. Now, what I've done in this section here now is, and we have kind of gone through some of these before, all right, is I've kind of got diagrams, right? And on these diagrams, what I'm going to do is I'm just literally going to ask you to kind of read the paragraph that I've then put on there, right? And then what we'll do is we'll have a little talk about it, okay? Because there's quite a few of them, right? So on here, firstly, we talked about the motor effect, right? So what I want you all to do is have a quick read of then what I've written, okay? Then we'll have a little talk, and then if anybody's got any questions about it, right, then we will.
So,
Hello.
what does it mean by keeping the forces in the same direction? Like that last bit.
Because you know when it goes past the split ring commutator, how the current then goes back, the current stays in the same direction. So therefore, if the current stays in the direction, the forces stay in the same direction. All right. So basically on that one there, right, what you're going to do is when you first start it, the force is going up. When it goes past the split ring commutator, because the current changes direction, the force stays up. Right? Or your motor will just keep on going backwards, forwards, backwards, forwards, backwards, forwards. Okay. This is kind of the reason why you have a starter motor in a car, right? Because what a starter motor in a car is, it's a very, very small motor that then provides a force to the main motor to make it start. Okay, so literally a starter motor makes or gives enough force to the main motor to make the main motor then start to spin. Right? Now, if you've ever made one of these in school, right, often what you'll do is you'll get it so that it kind of moves, right? But then it needs an additional little bit of momentum, a bit like an activation energy, to make it flip over the top. So then what will happen? It'll then do the spin, and then it gains momentum enough to then keep going. If you
And
get
so,
yeah.
how is the coil connected to the split ring commutator? Is it just like there, or is it like it connected physically?
It is. I mean, again, it's not the best picture, but you can kind of see the wire. There's two wires that come out of it, right? And
Hmm.
each one of those wires, right, is then kind of exposed. So
Okay.
really, sort of the split ring commutator does touch it, right? But it's just not a particularly clear diagram on it, right? But you've got
All
two
right.
wires coming out, which then are physically touched, and then it keeps swapping with the split ring commutator,
Okay.
all right? Okay.
So,
Yes,
what does the split ring like? What does it do?
it swaps that. You see on the actual diagram itself where there's a little gap in the actual split ring, right? So when that split ring, so if you kind of got a coil like that, right, what you've got is, so if I've got my commutator like that, and what it's doing is it's passing current. So let's say I've got it kind of here pointing towards the screen. This one here, the current is going towards you. All right. Now, as that spins, when it gets to the little gap, what happens is the current is then in my right hand, this hand, and then the current then goes into the screen again. Right. So I've got my split ring like that. Okay. This hand here, the current is going towards you. This hand here, the current is going towards me. All right. So then when the motor starts to spin, it gets to a certain point where it gets to the split and then the current changes direction again. So then when my hand gets to here, now this is my right hand, the current is going towards you, and the current on this side is then going away from you. So literally, when it passes the split in it, the current changes direction. Right? Did you make one at school, Zara?
I don't think so. I don't remember doing this.
I don't remember. God, you didn't make a motor.
No.
I know. Did you make one?
Sir tried to make it, and like the thing
Oh,
would
yeah.
stop working.
Yeah.
So
Right, yeah. Because with wish I had a better picture than that really. So with the actual motor, normally what you'll do is normally you'll kind of have a wire comes out of that there and out of that there, if you can actually see it. Okay. And then what you normally have is you kind of normally have another wire that kind of leans up against it. This is going to be a terrible picture. Right. In fact, I'm not even going to do that. Right. Basically with it is every single time it gets to kind of vertical, the actual piece of the actual motor itself, the current changes direction. And as soon as the current changes direction, the force stays going in the same direction. All right. So it's all about split ring commutator. And another thing, if they ask in the exam, you've always got to make sure that you've got a north and a south. Right. Again, I've seen that where they've actually drawn a diagram and they've had a north and a north. Right. And if you have a north and a north, nothing's going to happen. Okay. Right. So Zara, split ring changes the direction of the current. And if it changes the direction of the current, your Fleming's left-hand rule will always stay thrust going upwards. Right, next one, microphone. Have a quick read. right? So just to talk that one through. So what you then got, it's a microphone. Okay, now there's all sorts of different kind of devices that they could choose. So if you've got a sound wave heading in that direction there, right at the front of the the microphone, you've got a diaphragm. Okay, so the diaphragm is kind of some sort of sensitive layer that's kind of at the front of it, right? Then what you've got to do is you've got to think, if that diaphragm moves that way, because a sound wave has hit it, it's connected to the coil. So that coil then is connected to it. So therefore, if that coil is connected to the diaphragm and it moves that direction and it's on a magnet, you will then get an electrical impulse. And the electrical impulse will then pass down one of the wires, and then whatever the kind of system that's in there will then convert that to a sound. Okay, it'll then record it. So a sound wave makes the diaphragm move. The diaphragm makes the coil move. And because the coil is within a magnet system, electricity passes down the circuit. And then what you can do then is you can make the sound or record the sound. Okay, microphone. Now again, they could choose any diagrams ever, right? But what you got to do is you just got to think about, there's a coil. That coil is your electromagnet. Right, now whatever's going to happen, it's going to be something to do with the movement or the turning on and off of that coil. Right, so if electricity passes through a coil, it turns into an electromagnet. If electricity doesn't pass through the coil, it doesn't turn into an electromagnet. Right, now I think when we were doing this, we actually did the bell. Now I don't know if you can see in the bottom right hand corner, there's the bell. Okay, so the way that a bell works is that these blue lines here, right, are to the battery. Right, so if you imagine now that electricity passes through the, I'll just change the colour of my wire, of my pen. Okay, I'll do it green, green's lovely. Right, if you imagine electricity passes down that wire there, then what it does, it goes through this coil. What does that coil turn into? An electromagnet. Therefore, if this here becomes an electromagnet, and that there is made of iron, what it does is it attracts the iron to the electromagnet. The end of this, the armature here, dings the bell. As soon as that dings the bell, you follow the coil round, then what happens is, at this point here, there's a break. Then the electricity stops flowing, so the electromagnet turns off, and the bell then goes back again. Right? So again, just think about it. Electricity passes in here. That becomes a magnet. It attracts the iron. When it attracts the iron, that there breaks the circuit. And if the circuit breaks, the electromagnet turns off and the bell goes back again. Right. So now what we've got is, it looks like a motor, right? But this is now an AC generator. Right, so have a quick read, all right, and then what we'll do is we'll then have a little chat about it.
Sir,
Hello.
and it says the potential difference reverses direction.
Yep.
Does that mean it would like just go like this?
No, it spins round, okay, but what you've got is, because the actual wires themselves are fixed onto these, okay, they're not really split rings quite the same, right? Then what happens then is, when that spins, okay, it then almost passes electricity down that one and then down that one. It's almost like two kind of commutators that then will deliver the potential difference each time. So then what happens is the alternating current, it then goes up and down and up and down. Okay. So that is then an alternator, which then you'll have in your car engine again, right? And the idea of an alternator in your car engine is that it keeps charging the battery up. right? Based on your engine spinning in a magnetic field.
If you had an alternating current in like your motor effect, how come you need the commutator to make it go all the way around?
Yeah, but you haven't got an alternating current in your motor effect, it's direct.
Okay.
Okay, now we're gonna have a direct generator, a DC generator on in a minute. Okay. Right. A dynamo, which is your DC generator. So basically a dynamo is exactly the same as a motor, right? Because again, just like Adam was then saying then, is with a motor, there's literally only kind of one direction that everything is happening. So that is then direct. So a dynamo, right? Now people don't have dynamos anymore, right? But when I was a kid, right, what you used to have is you used to have lights on the front of your bike, right? And then that used to be then connected to your wheel. And on your wheel, you used to have another little wheel that used to spin on your wheel, right? So when you're pedaling along, right, then the little wheel that's on my sort of pedal bike, that used to spin and it used to make electricity, which is a dynamo. Okay. Now the biggest problem with that is when you stop pedaling, the light goes out. Right. I used to have like a dynamo torch where I used to kind of have a lever and used to press the lever like that. When you used to press the lever like that, you used to make electricity through it. It was a dynamo. All right. Right. Adam, you look so confused. I'm going to find the picture of a dynamo.
No, it's just like this concept in the alternator I can't get my head around. Like why one has the alternating current, why the other's direct.
Because on the alternating current, there is two full commutators. Right. So if you look at the bottom of this, there is two and they're not split. They are slip ring, right? Which basically means they are two full commutators, right? So basically what happens is when it spins, some of the electricity goes down the one, and then the following time, more voltage goes down the other. So there is no split to them. There is no change of direction. Okay. Then in the DC motor, right? The DC motor, you have got a split ring. So therefore, once it gets past a certain point, the current then stays in exactly the same direction. Okay, so as it spins in an AC one, you are constantly producing voltage, right? But then because it keeps on spinning in the same direction, the current then keeps changing because it's moving in the magnetic field. With a DC generator, you have got a split ring. So every time it goes past on the split ring, it produces voltage in the same direction. Okay. Right. So on a dynamo, what you've got in that bottom right-hand corner is that shows kind of the output from a dynamo, right? Where you've only kind of got positive voltage each time. Okay. Right. Transformers. Now, I think there was a transformer question, I think, on physics paper 1. Okay. So have a quick read of that. And then what we'll do then is we'll just have a little chat about it if we need to.
And so
Hello.
when it says a changing alternating current is supplied, is that just the alternating current itself?
Yeah. So what you got, if you look on
Okay.
the left-hand side there, where it's got kind of primary current, right? So when the current's going in, it's alternating. So it's going in way and then it's going back, right? So basically, it may well, I'm not sure of the exact time, but it may well be doing you 50 hertz. Okay, you know, your standard kind of electricity. So it'll be going into that, it'll be going one way, then turning the other way, right? And then what you have is you actually have a magnetic field that passes across. It's kind of carried in this is kind of like layers of iron, okay, which is the actual core. The magnetic field passes across, and because the magnetic field is also alternating, it creates an alternating current in this side as well.
Okay.
All right. Now, remember, with a transformer, okay, they're probably not going to ask anything again, right? It is all based on primary current, secondary current is all based on the number of coils. Okay, so if you've then got, let's say you've got 10 volts going in, right, and I've got 10 coils, and I've got 5 coils on the far side, what voltage am I going to get coming out? So I'll just ask the question again. If I've got 10 volts going in, and I've got 10 coils, and I've got 5 coils coming out, what would my voltage be? Right, so think about it. What sort of transformer is it? Lots of coils to less coils, it is a step down. Therefore, if it's a step down transformer, you know the voltage is going to go down. So theoretically, it'll be 5 volts. All right, and also remember that on this, if the voltage goes down, what happens to the current? The current goes up. Okay, hence why the whole point in the national grid is, and transformers themselves. And also, don't forget, the wattage on both sides stays the same. All right, so that is then a key thing that I don't think I've actually seen on an exam paper for quite a long period of time, is the wattage in the national grid stays exactly the same. Right, that's just another transformer one. Okay, right, now on to light. Okay, so if we then just sort of mention a little bit about light. Okay, reflection. Again, reflection doesn't particularly come up very much. They might ask you, the diagram that you kind of see where the incident ray comes in and the reflected ray comes out, it's exactly the same angle, right? For you guys, that is just probably the most obvious thing that ever happened. All right. Now, when that does happen, that is called specular reflection. Again, that is a word on the syllabus. Okay, specular reflection, right, is where it shines in and it's on a flat surface and it reflects off. Right, so remember that word, specular. Diffuse reflection is then where it hits a lumpy surface and it doesn't bounce off anywhere near as kind of ordered. So specular and diffuse reflection, right, are completely different. And you can see specular follows the rules, diffuse doesn't. Right. Lenses. I've only chucked kind of a few examples on these. I don't think they really ask particularly very much of these. Right. I think the most important thing is these words at the bottom here. All right. So if they do ask you to do a lens diagram, then wherever they tell you to kind of draw the object, the top of the object hits the lens, it goes through F, and then whatever happens, it comes down at the bottom there. Right, so if they ask you to do one of these lens diagrams, it starts at the top, horizontal, hits the center of the lens, goes through F, down to the bottom. Okay, the other one goes from the top, straight through the middle of the lens, in a straight line, and it goes down there. And then what you can then do is then you can then draw whatever your other object is. Okay, so then your other object is then drawn there. Okay, now the wording, real, inverted, magnified. Okay, so real is an object that you can actually see. Inverted, upside down. Magnified, made bigger. Okay, so I guess really that's a bit like our eyes, right? Where you've then got a object, it then goes through the lens on your eye. It's then inverted on the back of your eye. It's a real object because it's kind of made like on a screen. Then your brain then turns it upside down.
So,
Yes.
but if when you're wearing glasses, if the lenses itself inverts it, but then your eye inverts it again.
I don't think your lens, the lens of your glasses actually doesn't invert it. Right?
Okay.
If you hold your glasses away like that, it doesn't invert it.
Okay.
Right. Now there was an experiment that was done many, many years ago. Right. I may well have told you about this before. I can't remember. Right. Well, Adam's nodding at me, but I'll say it anyway because it's quite funny. Right. Where there was a guy, and what he had some lenses, some glasses that were put on his face. Right. And what he did was they inverted everything. So he was then walking around and everything was upside down. Right. He went to bed that night, and then when he got up in the morning, everything was normal. So he's still wearing the glasses, but everything was normal, right? So then he walked around with these glasses on and everything just looked okay. Took them off, right? And literally the whole world went upside down again, even though he didn't have any glasses on, right? And that's kind of like the power of the brain, right? Right. Another example, okay? This time is if the object then is within F, then what you can do is you can see the lines to a right, to the center, follow the line through, and it has to go through F here. Then top of the arrow goes through the center of the lens. Okay, so this time down on the right hand side, there is no object or no picture that can actually be made, right? Because a real object has to have a screen, or it can be seen on a screen. So therefore, this is virtual because the object gets shown up here at the top. It is upright and magnified. Okay, so it's a virtual, right? You can't actually see it. Final one is then with your big kind of concave lenses, where what you've then got is you've got your arrow, okay, goes to there and it gets bent upwards, goes through the center. So this time you get a virtual image because it cannot be shown on a screen. It is upright and it's diminished. Now, I don't think they're going to put a picture, diagram, anything like that on your actual exam, okay? But I think it's the words that are the most important thing. You've got real and virtual. So real can be seen on a screen, upright and inverted, and diminished and magnified. Okay, so they are kind of the 6 words that you need to use to describe something.
So,
Hello.
how do you know if it's upright or inverted?
So there's my arrow. That there is upright. It's the same direction. That there is inverted, upside down. Okay. So what you can do is, so where I've actually got these diagrams, if I show the first one again, right? So if I'm looking, I'll just clear all my scribble, right? So what I'm doing is I'm doing from the top of the arrow there. Okay, I'm going along there and I'm getting down here, and that is the point of the top of the arrow. So it's going top of the arrow to the lens, down, top of the arrow, through the center of the lens, down, and that is then where I will see the top of my arrow, right? And then what you can do then is, because the starting point is on the middle line, you can see that it's then drawn upside down. And if it's drawn upside down, that's inverted. Okay, and then if you actually go through it, right, and then you go through kind of this lens process and the arrow is still the same way, that is then upright.
How do you know if it's magnified or diminished?
Again, what you're going to do is, if you're going to get asked this or shown this, right, you literally draw the lines like I've kind of shown you on there, right? So if I look at this first one again, right, that's 2 squares, that's 3 squares. So therefore, what's happened to it? It's got bigger. So therefore, it's got bigger, it is magnified. Okay, the second one I put on, okay, where it's gone that size, you go through kind of the line process where you start at the top of the arrow and you go across to the center of the lens, through the F and go all the way down. Start at the top of the lens, go through the middle of it. They never meet. So if they don't meet, you then follow them back up here. And then you've got your arrow. And you can see that based on the fact that it has to start on the middle line, that arrow is now bigger. And it's also upright. Does that answer?
Yep. Thanks.
Right. Okay. Right. Light required practical. We've kind of talked about this a little bit already. Okay. So what we've got then is we've got reflection and refraction of light. Okay. Now, have I got a better diagram on that? Let me have a look. Did I put a better diagram on? Pants diagram, really, isn't it? Okay. Right. So we'll just go through it. Right. So incident ray. Okay. Incident ray is the ray that's coming in. Okay. That is then the one that is done using your kind of ray box. Okay. So you've got a ray box at the top that produces one beam of light. Incident ray comes in. And then what you can also see is the normal line is the line at 90 degrees to where your ray hits. Right. When it goes from less dense to more dense, which is the glass block, the incident ray turns towards the normal. Okay, so you can see it coming in. The beam of light comes down, goes from less dense to more dense. You can see where the normal line is. It then turns towards the normal. Okay. Then when it leaves, because it's going from more dense to less dense, there's another normal line there. It goes away from the normal. Okay. Right. I'm just going to add in another slide. Okay. Because so I just have to take that off the screen. So it's just kind of the sort of the logic of it. So the logic of it is, right, that if you've got what should we call it? We'll call it it's kind of the understanding of it, really, right? So what I've got there is that is mud. Okay, and my car, that's my car. It's got big fat wheels on it. Okay, it's heading towards that mud. All right. And what you've got to do is you've got to think that based on light, that is your normal. So your normal is at 90 degrees to kind of the mud. Now, as this car comes in and it actually gets to the mud, right, you've then got to think about what is logically going to happen. And logically, that wheel there is going to hit first. So therefore, if that wheel there hits first, what's that wheel going to do? Okay. That wheel there will slow down because that wheel there has hit mud. So therefore, if that wheel there has hit mud, the car will then turn. And what it will do, it will turn towards the normal. All right. So it's all to do with kind of like the slowing down of beams of light, waves of light. And that kind of illustrates the fact that it's the tire that then slows down, which then turns it towards the normal. Right. So remember your refraction. Incident ray, when it goes from less dense to more dense, the refracted ray turns towards the normal. When it comes out, it goes from more dense to less dense, so therefore it turns away from the normal. Okay, I think that's probably one of the easiest required practicals there is. Right, now just with waves again, right, double quickly, wavelength, peak to peak, trough to trough, same point on a wave, that is your wavelength. Amplitude is the height. Okay, and now what I'm going to do again is I'm just going to chuck in another slide. I should have just done this before. Right, just to then explain about sound. Okay, I started to do it in the other one, right? But right, so sound. If I've got that is my standard wave. Okay, and I've then got this wave. What can you tell me about that wave? So that is my normal noise. Dishan, what can you tell me about that wave there? So that's my normal. That's my comparison. What can you tell me about me hearing that wave there? Can't hear you. I can see your tash moving, but I can't hear you.
The first one, the pitch would be higher compared to the second one because of
So the pitch would be
frequencies.
higher in the top one.
Yeah, it would be higher.
Yeah, it would. So the pitch. So what I'm doing is that's my normal. So therefore, this one, it will be lower pitch. Anything else?
Period is longer on the second one.
Correct. What about the sound? Okay, so it's lower pitch, so it'll be deeper, right? What about the volume?
quieter because it's not as big as the first one.
Yeah, so the amplitude isn't as big. So it'd be lower volume because the amplitude isn't as big. Okay, then if I had this one, Farhan, what would that one be?
Which one?
This one. Okay, I'll just draw it again because it's not particularly very clear. So if I did that, what's
Yeah,
the sound going to be like this time?
it's gonna be loud
And
and high pitch.
high pitch, loud and high pitch. Okay, right. And again, they might do a comparison of it. I don't think they will. Okay, louder, quieter, right? Higher pitch, lower pitch. Okay, so that
So-
kind of works. Yes,
So just to double check, your amplitude is the volume
correct.
and your wavelength is the pitch.
Correct.
Okay.
Right. So hence, when I was kind of talking about before, you know, like 30, 40 years ago, whatever it was, we used to have a record player, right? A tape player and an amp, right? And the amp, which was basically the thing that controlled the amplitude, was the volume one, right? So amplitude is the volume, pitch is the wavelength, all right? Right, so that is then the two waves, and I talked about those before. Now remember, transverse wave, the particles are moving, Daniel, so the particles are moving in a transverse wave. What word did I say, beginning with a P?
Perpendicular.
Good, right, and Daniel, the longitudinal ones are moving.
Parallel.
Well done. All right, so they're, again, the same examples, right? Zara, give me two examples of a transverse wave.
Sound wave.
Nope.
Oh, I can't remember any.
Right, transverse wave is light and water. All right, now I'm quite glad I asked that question, really, right? Because loads of people think that the transverse wave is a sound wave, but it isn't, right? So you know when you see on the TV and stuff like that, where you see people's heartbeats and things like that making sound, that's because it's computer generated. So a longitudinal is a sound wave because it is a pulse. It's a pulse of the particles. All right. And then what they do is on computers, they convert those sound waves to a transverse wave to make it look more kind of visible. So a sound wave is a longitudinal wave. And remember, rarefaction and compression. The wavelength on here is from a rarefaction to a rarefaction. A compression or a wavelength again could be from a compression to a compression. Right. Now, sounds in a solid. Okay, this was again something that I didn't have on my PowerPoint. So what I did was I chucked it in. Okay, so it just kind of talks about the transfer of sounds between solids and gases. So basically what I've got is I've got a rod of metal hanging. I hit it with a hammer. Okay, so therefore what's happening is the particles are moving in there. So as your longitudinal wave, and when it gets to the end, the particles in the metal are then transferred to waves in air. So it's basically the transfer of particle energy. All right, so that is then sound going from a solid to air. Okay, and it also kind of makes sense that sound travels faster in a solid because the particles are closer together. Ultrasound, okay, again, it kind of works, you know, the same sort of way that we've kind of talked about before. So you've got a sender, and that sender sends waves, ultrasound waves, to an object. When it hits the object, the sound waves bounce back, and a computer then can work out exactly what is happening. Okay. Right, now another kind of GCSE question, right, that came up was about fishing. Okay, it's just something to think about. Right, so there's the water, right, and we've got a boat on there. Okay, there's a boat, right, and what they wanted to do is they wanted to know how far it was from the boat to the bottom of the sea. Okay, and what they did was they said, what did they say now? They said the speed of the sound wave was 200 meters per second. Okay, and the time it took was 10 seconds. All right, so this is then an exam paper that loads and loads of people got wrong. It was 3. So what they did is they used ultrasound, okay, to find the depth of the water. The ultrasound that came out of the boat traveled at 200 meters per second. And the time it took for them to receive it was 10 seconds. So therefore, how deep is the water? Okay, who shall I pick on? Daniel. How are we going to do that?
What's the question?
Right, you've got a boat that sends ultrasound down, right? And the idea is to find the depth of the water. The ultrasound travels at 200 meters per second, and it takes 10 seconds for them to get back a sound, right? So therefore, how deep's the water? Speed equals distance divided by time. Right, so speed is 200. Time it takes is 10 seconds. How deep's the water, Daniel?
2,000.
2,000. Okay, so speed 200. I'm just going to do it over here. 200 multiplied by 10 seconds is the distance. So 200 is 2,000 meters. Okay, 70 something % of the country got that wrong. All right,
So
as have you,
awkward
Daniel.
question.
Daniel, how come you've got that one wrong? I'll ask the question again. How deep is the water?
Wait, do you divide it by 2?
You do. Okay, right. So again, it's just kind of an example of a question, right? And you do divide it by 2 because obviously it takes from there to there 10 seconds, right? Right, black body radiation, right? Have a quick scan of that, please. Right, quick read. Okay. Sometimes it's called the perfect black body radiation, right? But basically, what is going on with that is you have a black object, and what it does, it absorbs all of the radiation. Okay, so all of the electromagnetic spectrum radiation, it absorbs it all. And then once it gets to a certain temperature, what it then does is it emits thermal radiation. Okay, because what it's got hot. Okay, not really quite sure of the point in this, right? However, right, the point of it is that the black body absorbs all of the electromagnetic spectrum. That, when it absorbs it, it then turns to thermal radiation that it then emits. Okay, and that is
So-
about, yes.
Would that make the Earth a black body because then it it emits infrared?
Well, no, because the Earth. So some of the electromagnetic spectrum that hits the Earth just gets reflected straight back off. Right,
Okay.
where if the Earth was black, completely black, then it would be this case. Okay, right. P&S waves in earthquakes. Okay, so what we've got is we've got a P wave, which is our longitudinal. So again, when I asked Zara for examples before, a longitudinal wave is sound and an earthquake. And we know it's an earthquake or we know it's a longitudinal because it's got compressions in it. Right? So think about it now. What it is, it's where it hits. Okay. And if you imagine if you had a little house there now, right? Then, and that is then got a P wave underneath it, that house is going to go backwards and forwards. Because, like Daniel told us before, the vibrations are parallel, so they're going backwards and forwards. All right. So that is then a P wave. An S wave is your transverse wave. So now imagine if you had a house there, right? What would happen to your house there is it would go up and down. Hence why earthquakes are so bad, is because when you've got an earthquake that's an S wave and a P wave, your house goes up and down and it goes backwards and forwards. So therefore, what's going to happen is if it was in certain circumstances, then your house would have been in a huge amount of trouble. Right? So you've got P waves and you've got S waves. S waves is transverse. Right? On the Earth, so there is the epicenter right at the very top. Okay, and then in the kind of the liquidy bit will only take the S waves. Okay, so the liquid bit will take the S waves, and also the liquid bit will take the P waves. So the S and the P waves go through the liquid, and you can see kind of my diagram there, right? And then the P waves, which are longitudinal, will pass through all of it. Okay, because P waves, they can then pass through any kind of core, any sort of substrate, right? Where S waves, yeah.
But if the S waves can go through liquid, how come it can't go through the liquid core?
Because what's in between the liquid core and what's between this bit and the liquid core?
But
Okay.
like,
If you think about it, right, that bit there is liquid.
Hmm.
That bit there is but it's all to do with it's all to do with the density of the liquid as well, isn't it? Right? Because what you've then got is you've got the S waves can then travel through kind of the sort of the less dense liquid, right? Where when it gets to the liquid core, right, then it then can't travel through those kind of levels of density of the actual liquid itself. And then the P waves then will go all the way through. And the P and the S waves, they also travel at different speeds. So for example, that's a comparison diagram. Primary, right, will go through liquids and solids, the P waves. The secondary will go through solids only. So that's what I'm talking about. You know, I guess this point now where I've been talking for 3 hours and my head goes to mush, right? So the S waves will only go through the solid, and that's the solid there, isn't it? Okay, where the P waves will go through solid, liquid, which is that bit there. All right. So the fact that the S waves won't go through liquid. All right. So P waves through liquids and solids, secondary waves just through solids. P waves travel at 8 kilometers a second. S waves travel at 4.5 kilometers per second. Space. Final little bit. This is quite small, this bit. Okay. How does an object stay in orbit? Right. So if you think about it now, right. So what we've got there is you've got Earth, and then what you've got is you've got a satellite going around the outside. And what there's something called a centripetal force, right? Where that is then the force that is then being dragged down. Okay. But because it is also going at a certain speed, the velocity keeps it going in orbit. So basically what's happening is that satellite is constantly falling towards the Earth, but because it's also traveling sideways as well, they compensate for each other, and then it keeps on going around in a circle. All right. So the further away that it is from the center, the slower that it goes. Okay. So centripetal force is the reason why it doesn't plummet towards Earth. Solar system. My very easy method just speeds up naming. Okay, obviously there's no Pluto anymore. So Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Okay, Right, now, life cycle of the star is kind of the biggie bit. Okay, right, so what you just need to do is you just need to think about the two paths. So starting on the left-hand side, what we do is we start off with a giant nebula. Okay, so basically what that is, that's a massive, great big cloud of stuff. Because it's so big, the gravity pulls it all in and it becomes a protostar. And what a protostar is basically a star that is then getting ready to be born. It then goes to the Tauri phase, which is then where the actual star does become. Right? The protostar is kind of the most important section on it. Right? Now, two routes that it can go. When it comes out, it can either go be a massive star, right, where it actually makes our star look like a teeny weeny little dot. So the main sequence star, like Sirius, is a massive, massive star. And eventually, when it gets a little bit older, it starts to then become a red supergiant. Eventually, when it becomes a red supergiant, it explodes, collapses in on itself due to gravity, and becomes a supernova. Eventually, when the gravity has dragged it in so much, it can either become a neutron star, which spins at an incredible speed, or a black hole, which basically has so much gravity it doesn't even let light escape. The other route is like ours, which is a sun. That then, over time, will become a red giant. Right? Now the question is, why does it actually become a red giant? Because what you have is you have the sun, and for the sun to stay as it is, what you have is you have the outward force of fusion, and you have the inward force of gravity. Okay, so fusion is constantly trying to make it get bigger. Gravity is then constantly trying to make it get smaller. And eventually, when the hydrogen has turned to helium, right? And eventually what happens is the fusion then becomes big enough that the then whole sun starts to get bigger and it becomes a red giant. Because then the fusion force is bigger than the gravity force, which then makes it get bigger. Right? And eventually when that happens, Earth will just get swallowed up. The red giant finally explodes and becomes a planetary nebula, then a white dwarf, which is hot, then finally a black dwarf, which is a hot white dwarf that's cooled down, and then literally what it is, it's an incredibly high density object. Anybody got questions about that?
Sir, can you explain like the hydrogen bit again?
I will. Right, so if we've got our sun, okay, shut up, phone. Okay, so what we've got is we've got our sun at the moment, right? And what we've then got is currently hydrogen is fusing into helium. Okay, and what that does is that is an outward force of fusion, right? Which is basically a nuclear explosion that's happening. Right, so it's constantly hydrogen is then getting fused with helium, creating loads of energy, and it's basically making an explosion. So therefore, you'd imagine that the whole thing would blow up. But then, because of the immense size, the gravity of the sun keeps it all in place. So they kind of counteract each other, giving it to the kind of the same size. Eventually, when the hydrogen starts to run out and then they start fusing helium, the fusion reaction then gets bigger than the gravity. And then what will happen is, as the fusion reaction gets bigger, the sun will get bigger, and eventually it'll then turn into a red giant. Okay? And then that'll be the sun getting bigger and bigger and bigger, and gradually what it'll do, it'll just sort of take over the whole of the solar system, and Earth will then get just submerged. Okay, so it's like a comparison between fusion and gravity. right? Okay, right. Big Bang, right? So depending on people's religious states, okay, so Big Bang Theory states that the universe began from a very small initial point. Okay, it's quite mind-blowing to think that it might have actually done that. Okay, I can't remember now. Is it something like 42 billion, 62 billion years it's supposed to be? So it kind of starts off in the central point, it explodes, and then they think that it gets to a certain point, and when it gets to a certain point, it's all going to get dragged back again. Okay, and then it's going to go back to a big bang. Right? Evidence is redshift and blue shift. Okay, Farhan, do you know what redshift is?
Redshift is essentially like is it like the Doppler effect of the planet? So it's moving away, and the waves are like moving further away, which proves that the universe is expanding.
Yeah, that's exactly it. So what you got is you've got your normal kind of visible light, red, orange, yellow, green, blue, indigo, violet, and because it's moving away, the red band stretches. So therefore, what it does, it looks red, right? But then you've also got the blue shift, right? And the blue shift is where you actually can look at something, and if it looks blue, that means it's heading towards you. Because this time, the red, orange, yellow, green, blue, indigo, violet, right? The blue section is getting stretched, so therefore you can see more blue. All right, so evidence of the Big Bang is redshift. Okay, and that tells us that galaxies are moving away. The further away the galaxy, the more it is redshifted. Okay, and it's also to do with the speed. The faster it's going away, the more redshift there is. Cosmic microwaves, right? What we've got, those got those detected all over the place. And what they think that is leftover heat from the Big Bang. If you imagine the whole of the universe blew up in one point, that must have been a reasonably energetic kind of point. Right? That's then showing it again, right? Basically what Farham told us, redshift and blue shift. That's then kind of a diagram of kind of an electroscope of hydrogen, right? Where you've got hydrogen, and then because the red shift at this bottom one is a lot bigger, then you've got a lot more red light that is then being provided. And then that is it. Oof. Right. Anybody got any questions about anything? Again, I think we've covered whole of, well, half of physics tonight. Right. So just don't forget your sums. All right. I know you're all dead good at maths, right? You're all completely and utterly amazing at maths, right? So please don't forget them. All right. Take your time with it, right? And then just answer whatever it asks you. Right. So again, anybody got any questions? Right. Seriously, well done, everybody. Right. You've been completely and utterly amazing, right? For however long it's been. Okay. And what you need to do is on results day, right? Make sure you send me your results. All right. Obviously, I can find out a couple of people's, right, and nag them. All right. However, everybody else, can you please send them? Right, so I can see how you've done, because I am actually genuinely interested. Okay, especially for people that have been truanting and wagging for about the last 3 years of their lives. Hey, Farhan. Not you, no, not you. Right, well done, everybody. Okay, I am going to put this up onto Google Classroom, right, if anybody ever wants to kind of look at it, right, but it'll take me about an hour because it takes that long. All right, so thank you, Bawaji, Alex, Zara, Zishan, can't see you. Right, I will hear from you at the end of August. Well done, everybody.
Thank you, sir.
Bye.
Cheers.
Bye.
Yeah.
See ya.
Bye, sir.
Yeah.